Hello there and welcome to Science for Sleep, where curiosity settles in beside you and science takes its time instead of rushing ahead. Tonight we're heading somewhere unusual, not far away like distant galaxies or black holes, but inward, towards something so small it barely seems possible that it exists at all. It's a place where distance stops behaving like distance, where space itself might lose its familiar meaning, and where the rules that guide everything we know become uncertain in ways that even physicists find difficult to describe. We're going to explore what really happens at the Planck length, the tiniest scale the universe allows, a scale so minuscule that if you try to imagine it, your imagination would probably shrug and ask for a simpler assignment. Before we go there though, I'd love to know where you're listening from tonight. Maybe you're stretched out under blankets, maybe you're curled up on the couch, or maybe you're unwinding after a busy day. Wherever you are, what time is it in your corner of the world? Fitting in a way, because talking about the smallest possible length means talking about the foundations of space and time at once. And if this gentle wander into physics helps you relax, or keeps your mind occupied just enough to drift comfortably into sleep, I'd be grateful if you gave the video a like or maybe subscribed. It helps this quiet little space find others who enjoy learning in a calm, unhurried way. So let's begin the slow descent into the Planck length, easing into it bit by bit without expecting our minds to grasp it all at once. After all, the Planck length is so far removed from everyday experience that even imagining something a million times larger would still leave us thinking about something impossibly tiny. But that's all right. You don't need to picture it clearly. You just need to let the ideas sit with you, slowing down your thoughts and letting the strangeness of the very small carry you deeper into the story. When people talk about the size of things, we usually rely on comparisons our minds can latch onto. A grain of sand, a strand of hair, a cell, a molecule. Even when we get down to atoms, we can still navigate the scale with some effort. But then quantum physics arrives and tries to take us much smaller into realms where particles behave both like objects and waves, where position and momentum can't be pinned down exactly, and where the comfortable rules that help us make sense of daily life no longer apply. Even so, quantum physics still deals with scales far larger than the Planck length. If an atom was stretched to the size of the visible universe, the Planck length compared to that atom would still be unimaginably smaller. It's a scale so extreme that our usual measurements, built from meters, millimeters, and nanometers, aren't just inconvenient. They're meaningless. And yet the Planck length isn't just a random number physicists invented to impress their colleagues. It arises from three fundamental constants of nature that seem completely unrelated at first glance. There's the speed of light, which sets the ultimate speed limit for anything travelling through space. There's Planck's constant, which controls the graininess of quantum behaviour, and there's Newton's gravitational constant, which sets the strength of gravity. If you take these constants and combine them in just the right way, you get a length so small it becomes the threshold where space and time themselves may stop functioning the way we expect. Below this length, the familiar idea of distance may not exist at all. This gives the Planck length a special role in physics. It isn't the size of an object or a particle, it's more like the limit of what space can mean. It's the point at which the universe seems to say, any smaller than this and the usual rules won't help you. At this scale, the smoothness we think of when we imagine space starts to break down. If you zoom in far enough, the universe stops looking like a well-behaved grid and begins to resemble something turbulent, shifting and unpredictable, like the surface of water seen under extreme magnification. The Planck length is the point where the large-scale structures we understand lose their reliability, and the rules of quantum mechanics and gravity begin to compete with each other in ways we can't fully describe yet. But before we sink deeper into what might happen at that tiny boundary, it helps to acknowledge just how far removed it is from anything we can measure directly. The smallest distances we can probe with our most powerful particle accelerators are still millions of billions of times larger. Even imagining technology that could reach the Planck scale feels like imagining a microscope that could see individual seconds, or a telescope that could examine the past with perfect clarity. Still, physicists explore the Planck length not by building such tools, but by thinking carefully about the equations that shape the universe. When these equations break down or contradict each other, the Planck length often appears like a signpost marking the point where a new theory is needed. At this scale, ideas that seem separate in everyday life begin to merge. Space is no longer a quiet stage. Time is no longer a simple flow. Matter is no longer something with a definite position. And gravity is no longer the smooth curvature Einstein described. Everything becomes uncertain, jittery, and interwoven. This chaotic jitter isn't just a convenient picture, it's a genuine prediction of quantum physics. The smaller the scale, the more energetic and unstable space becomes. If you try to isolate a region of space a Planck length across, the energy fluctuations within it would be large enough to create tiny black holes that form and evaporate almost instantly. Scientists sometimes call this chaotic environment quantum foam, not because it's frothy in any literal sense, but because the constant bubbling of energy makes space behave less like a solid fabric and more like something alive with fluctuations. Of course, descriptions like this can give the impression that space at the Planck length is simply messy, as if it's just a more complicated version of what we already understand. But the truth is stranger. At this scale, the concept of space having a definite structure or geometry might not apply at all. Space may not be composed of continuous points. It may instead be made of discrete units, tiny, indivisible bits that can't be subdivided further. If that's true, then the Planck length would be the smallest meaningful measurement of distance, not because space refuses to let us look closer, but because there simply isn't anything to look at on a smaller scale. Asking what happens below the Planck length might be like asking what's north of the North Pole. The question itself may not make sense. This idea of discrete space raises interesting possibilities, but it isn't the only way physicists try to understand the Planck length. Some theories propose that space becomes fuzzy, losing sharp boundaries. Others suggest that space might twist and warp into strange shapes. Some theories propose that space isn't fundamental at all, but emerges from deeper patterns or relationships that don't involve distance in any conventional way. When researchers consider these possibilities, they often find themselves dealing with a universe that behaves differently from what we intuitively expect. And while the details vary, many of these theories agree that the Planck length marks the point where classical geometry stops being reliable. All of this might sound very removed from daily experience, but it connects to simple questions. What does it mean for something to have a location? How do we define the boundary of an object? What is motion at the smallest scale? We often assume that space is the backdrop that gives clear answers to these questions, but if space itself has a minimum size or a structure that changes at tiny scales, then even the meaning of motion becomes unclear. An object might not move smoothly from one point to another. It might jump, blur, or exist in a way that doesn't align with our usual understanding of movement. Someone listening to this might wonder whether this tiny scale affects anything in everyday life. For the most part, it doesn't. The Planck length is so far below the scale of atoms, molecules, and even subatomic particles that its effects are drowned out by the larger rules that govern those realms. But the Planck length matters because it seems to lie at the root of how those larger rules form. It acts as a foundation beneath the quantum world, and even though we don't directly interact with it, our entire universe depends on whatever structure exists there. That structure becomes especially important when physicists study systems where quantum mechanics and gravity both matter. Black holes are a good example. Their centers, often described as singularities, are places where the density becomes so extreme that gravity overwhelms everything else. Classical physics predicts that these singularities have zero size and infinite density. But most researchers believe that this can't be correct. Instead, many suspect that the Planck length imposes a limit, preventing a singularity from collapsing indefinitely. If that's true, black holes might contain cores no smaller than the Planck scale, and understanding those cores could help solve many outstanding mysteries in physics. These mysteries include questions about information, entropy, and the structure of space-time itself. Some theories propose that the Planck length plays a role in the holographic nature of the universe, the idea that the information content of a region of space depends on its surface area rather than its volume. If this idea holds, it might mean that the world we see as three-dimensional is actually encoded on a two-dimensional boundary at the smallest scales. Other theories suggest that space-time arises from networks of interacting elements that naturally have a minimum size built into them, making the Planck length not just a property of space, but a property of the deeper structure that generates space. It's a lot to take in, especially when the goal is to relax rather than to wrestle with the most difficult questions in physics. But there's something soothing about recognizing that even the tiniest scale of the universe contains layers of complexity we're still trying to understand. The Planck length isn't just a number, it's a gateway to an entire landscape of ideas, each trying to explain what lies beneath the familiar world we know. And while we're far from having definitive answers, the journey toward understanding this scale helps shape our broader picture of reality. There's a comfort in knowing that the universe keeps surprises hidden in places we can't see, tucked away not just in distant stars but in the very fabric of the space around us. And the more we learn about these hidden structures, the more we appreciate the depth and richness of the world we live in. Even if the Planck length is far beyond anything we can touch or measure, thinking about it brings a sense of quiet perspective. It reminds us that our everyday experiences are built on foundations so intricate and so finely tuned that they seem almost improbable, yet here they are, supporting everything we do. When people talk about the measurable universe, the thoughts usually drift toward telescopes pointed at distant galaxies, or detectors waiting for faint whispers of particles that pass through everything. It's natural to picture the largest possible scales, the kind that stretch imagination outward rather than inward. But the measurable universe also has an edge on the opposite side, hidden not in the sky, but inside the limits of the instruments and methods we use to look into the small. That edge sits far above the Planck length, but it still marks a frontier where the world becomes less cooperative, where measurements start to stumble, and where the gap between what we can observe and what actually exists grows wider with every attempt to look closer. At first glance, it seems simple. Look at something small with a stronger microscope, then use a better one, then use an even stronger technique until you reach the point where nothing remains hidden. It's a comfortable idea, the sense that with enough tools and effort, you could peel away the layers of the universe like layers of an onion. But the real world doesn't arrange itself so neatly. The universe wasn't designed to let us look at every detail at any scale, and the rules that shape matter at very small distances make the process of measuring itself increasingly complicated. The earliest microscopes opened a new window into worlds that had been invisible for all of human history. Once those tools were invented, the idea of something being too small to study began to fade. Each new instrument seemed to push the boundary a bit further, but even those early advances hinted that the small behaves differently from our everyday surroundings. When scientists looked at tiny structures of living cells, crystals, or bacteria, light stopped being just illumination and began behaving like a tool with its own limitations. Even at that level, certain details could never be made sharper, because light itself has a wavelength. Shine light with a wavelength larger than the thing you're trying to see, and all you get is a blur. You can't see finer details because the tool you're using washes them out. To overcome those limits, scientists tried shorter wavelengths, pushing beyond visible light into ultraviolet. Then came electron microscopes, which use waves associated with electrons rather than light. Because electrons have much shorter wavelengths, they can reveal much smaller features. With those tools, the achievable resolution moved from micrometers to nanometers, and then even smaller. Suddenly, atoms or small groups of atoms were no longer theoretical constructs in textbooks. They became visible structures, patterns, lattices, arrangements that could be mapped and measured. But even electron microscopes run into a wall eventually. The smaller the scale, the more energy you need to probe it. Push electrons to higher energies so they can resolve smaller structures, and eventually the interaction between the electrons and the material becomes so intense that you start to alter or even destroy the thing you're trying to study. Measuring something so small begins to interfere with the measurement, not because the instruments are clumsy, but because matter itself responds to high-energy probing with unpredictable behavior. This idea shows up long before you reach the Planck scale. It begins at the level of quantum mechanics, where trying to determine a particle's position more precisely introduces uncertainty into its momentum. The Heisenberg uncertainty principle isn't a limitation of technology. It's a fundamental feature of the universe. It tells us that certain pairs of measurements can't both be sharp at the same time, no matter how good our tools become. And that uncertainty grows as we push towards smaller and smaller scales. To measure or visualize a tiny region of space, you need a particle or wave that can interact with it. The smaller the scale you want to probe, the shorter the wavelength that's required. To get such short wavelengths, you need high energies. But when the energies become extreme, the particles you use begin to disrupt the system in ways that make precise measurements impossible. The act of looking stops being separate from the thing you're looking at. Instead, it becomes part of the process, stirring up the very region you're trying to examine. This is why particle colliders became the next stage in the journey toward the small. Instead of trying to gently observe tiny structures with light or electrons, scientists decided to smash particles together at enormous energies and study the fragments that came out. The higher the energy of the collision, the smaller the distances they could probe indirectly. That method led to the discovery of quarks, gluons, and a host of particles that live inside atoms. But even these methods have limits. The energies required to reach smaller distances grow faster than our ability to build machines that generate them. The Large Hadron Collider, the most powerful particle accelerator ever built, can reach distances thousands of times smaller than an atom. But even this impressive machine is still many orders of magnitude away from the scales where quantum gravity becomes important. To probe the Planck length directly with a collider, you would need a device the size of the Milky Way, powered by energy far beyond anything our Sun produces. It's not simply difficult, it's physically unrealistic for any civilization we can imagine. So the edge of the measurable universe isn't defined solely by the abilities of our tools, it's shaped by the rules of physics themselves. At small enough scales, measurements are no longer gentle inquiries. They become energetic events that fundamentally reshape the thing being measured. And the closer you get to the Planck length, the more severe this interference becomes. Trying to measure a region of space that's small would concentrate enough energy into a tiny volume that the measurement itself might create a miniature black hole. The act of looking closer would collapse the space you are trying to observe. This boundary is not arbitrary. It emerges naturally from the combination of quantum mechanics and general relativity. According to quantum mechanics, probing a smaller space requires higher energy. According to general relativity, concentrating enough energy into a small enough region causes it to curve into a black hole. Combine these two rules, and you get a boundary. Below a certain size, any attempt to measure space collapses that space into something else entirely. That size is close to the Planck length. Because of this, no microscope, no collider, and no instrument built of matter can directly access these tiny distances. The measurable universe ends long before the Planck length begins. There's a region of space where the rules of measurement stop applying the way we expect. We know the physics isn't smooth at that point, but we don't know exactly what replaces that smoothness. We're looking at the shoreline of a continent we can't yet map. Even so, the edge of the measurable universe is not a dead end. Instead, it acts as a bridge between what we can study and what we can infer. While we can't measure distances near the Planck length directly, we can explore mathematical theories that attempt to describe what lies beneath that threshold. These theories are built on extrapolations, principles, and symmetries that hold at larger scales. They stretch those principles downward, trying to see where they break, and then adjusting them to remain consistent. Sometimes these theories produce intriguing predictions. Sometimes they contradict themselves. Sometimes they point to entirely new interpretations of space, time, or matter. What's interesting is that different theories approach the Planck scale from different angles, but they often converge on the idea that classical space can't exist that far down. Some theories suggest that space-time becomes discrete. Others suggest it becomes fuzzy or uncertain. Still others propose that space-time is not a primary ingredient, but something that emerges from more basic elements that behave according to unfamiliar rules. These theories differ, but they all agree that the edge of the measurable universe is not simply a technical inconvenience. It's a sign that our current understanding of reality has gaps, and the Planck length marks one of the largest ones. People often imagine the smallest scales as being similar to the largest ones, just with tiny versions of galaxies or atoms arranged like miniature cosmic structures, but the truth is far stranger. At extremely small distances, familiar shapes and relationships disappear. The idea of a location becomes uncertain. The idea of distance becomes difficult to define. Time itself stops flowing smoothly, and interactions that are separate at large scales become tangled together at small ones. One way to understand this is by thinking about energy. Energy is required to measure or probe space, and energy itself influences space. At large scales, these effects are subtle, but at small scales, they become intense. Space responds to the energy you put into it, shifting its curvature, stretching, or compressing in unpredictable ways. Time behaves similarly. It can speed up or slow down depending on the energy conditions. The smaller the region you try to isolate, the more the energy fluctuations dominate the behavior, making it impossible to define a clear boundary or a stable structure. This effect doesn't appear all at once. It grows gradually as you move deeper into the quantum realm. At the scale of atoms, measurements become slightly uncertain. At the scale of quarks, patterns emerge, but only statistically. Move deeper still, and the distinction between particle and field begins to fade. Keep going, and the classical idea of space breaks down entirely. The measurable universe ends not because there's nothing smaller, but because the concepts we use to define size stop working. If someone asked whether something exists smaller than the smallest measurable distance, the honest answer would be that we don't know. There might be structures below that boundary that shape the universe in ways we haven't yet imagined. Or the universe might be built from a minimum unit of space-time that cannot be subdivided, in which case asking about anything smaller than that unit would be like asking about fractions of a pixel on a digital screen. The pixel is the basic unit. It has no smaller interior. Either possibility is compelling. The first suggests an endless depth of structure hidden behind the limits of measurement. The second suggests that our universe has a smallest building block, a foundation on which everything else stands, and we haven't yet discovered which one is correct. Still, the boundary itself is useful. Knowing that our measuring tools cannot cross a certain threshold gives us a place to focus theoretical work. Instead of trying to directly probe an impossible distance, we explore the consequences of different assumptions about that distance. If space is discrete at extremely small scales, what patterns would emerge? If space is continuous but chaotic, how would particles behave? If space is not fundamental but emerges from deeper processes, what predictions would follow? The edge of the measurable universe becomes a testing ground where theories compete. A theory that predicts impossible behavior above that boundary is easily ruled out. A theory that smoothly approaches the boundary without contradiction stands a better chance of describing what lies beneath. And while no current theory fully combines quantum mechanics and gravity into a single, complete picture, several promising candidates continue to evolve. The edge of the measurable universe not only marks a technical boundary, but also an intellectual one. It challenges assumptions about what science can know. It reminds us that knowledge isn't simply a matter of building better tools. Some questions require new frameworks, new languages, or new ways to think about the world. As we move deeper into the story of the smaller scales the universe allows, it becomes natural to ask why the Planck length exists at all. It's one thing to say that space becomes difficult to measure at that point, or that our tools break down, or that equations start to misbehave. But none of that fully explains why the universe seems to draw a boundary there. It raises an interesting question. If the universe could have allowed distances to continue shrinking forever, why doesn't it? Why is there a limit beneath which the concept of space begins to lose meaning? This question matters because the Planck length isn't just a number someone invented. It's not a measurement based on something we've directly observed. It comes from the natural constants that describe the universe in its most basic form. These constants appear repeatedly in physics, shaping everything from the speed of light to the behavior of atoms and the force of gravity. When you put them together in a particular way, you get a length so small that it suggests the universe has a built-in minimum scale. And once you see how these constants interact, the existence of such a limit begins to feel less like a random choice, and more like something unavoidable, woven into the structure of the physical world. To understand why this boundary exists, it helps to start with the constants themselves. The first is the speed of light, which acts as a universal speed limit for anything moving through space. It's not just a property of light, it's a property of space-time itself. The second is Planck's constant, which controls the scale of quantum effects, telling us that energy comes in small bundles rather than smooth, continuous amounts. The third is Newton's gravitational constant, which determines how strongly masses influence each other through gravity. If you combine these three constants mathematically, they form a length, a time, and a mass. These are called Planck units, and they describe the universe at its most extreme conditions. The fact that these constants can be combined to produce a length at all suggests something interesting. The Planck length isn't derived from the size of a particle or the structure of matter. It comes purely from the relationships between the fundamental rules that describe everything. That's what makes the number special. It isn't attached to any one phenomenon. It arises naturally from combining the most basic principles of physics. But why do these particular constants create this boundary? What is it about their combined effects that forces the universe to set a lower limit on the size of meaningful distances? One way to answer that is by imagining what happens when we try to measure something extremely small. To resolve tiny structures, you need high-energy probes, because high energy allows you to create short wavelengths capable of interacting with very small regions of space. But as the energy becomes higher, gravity becomes stronger. Gravity isn't usually a concern at the scale of atoms or electrons, but as you keep increasing the energy to investigate smaller and smaller distances, the gravitational effects start to matter. Eventually you reach a point where the energy you inject into a tiny region of space becomes so large that the region collapses into a miniature black hole. Instead of revealing smaller details, you create a dense object that hides them. This natural limit means that trying to study space below a certain scale leads to gravitational collapse. The Planck length appears as the distance at which this collapse becomes unavoidable. It arises from the balance between the energy needed to probe a region and the gravitational effects of that energy. Because of this balance, the Planck length acts like a boundary where quantum mechanics and gravity are equally important. It's the scale where the usual tools of physics fail not because they're flawed, but because the universe itself prevents anything smaller from being accessed. Another way to think about it involves uncertainty. Quantum mechanics tells us that the more precisely we try to determine something's position, the more uncertain its momentum becomes. When we push the uncertainty in position to extremely small values, the uncertainty in momentum grows until the particle we're trying to observe acquires so much energy that it changes the very space it occupies. The Planck length emerges from this uncertainty, marking the point where space can't be squeezed any tighter without altering its fundamental nature. So the Planck length exists because quantum mechanics demands that energy increases as localization becomes more precise, and general relativity insists that enough energy distorts space-time. When you combine those two demands, you get a minimum size that prevents space from being subdivided indefinitely. The Planck length isn't something arbitrary, it's a consequence of the rules we already know. A different approach comes from asking what space actually is. Many modern theories suggest that space isn't a continuous fabric, extending smoothly in all directions but might be composed of discrete units. If that's the case, then distances smaller than the Planck length might simply not exist because the universe has no smaller building blocks. Just as you can't cut a pixel into smaller pixels on a digital screen, or divide a molecule of water into smaller units that behave like water, you might not be able to divide space into smaller pieces without losing the meaning of distance entirely. In this view, the Planck length is like the smallest step on a staircase. You can go up or down, but you can't take half a step without falling between the steps. If distances are composed of discrete increments, then the Planck length marks the smallest possible increment. Any attempt to measure something smaller doesn't fail because we lack the right tools, but because the concept itself doesn't apply. There is also an argument based on the behavior of fields. Everything in the universe is made of fields, and particles are excitations of these fields. At large scales, fields look smooth, but at extremely small scales they become violent and unpredictable. Energy fluctuates wildly, particles appear and disappear, and the structure of space-time seems to jitter. This jittering becomes more intense as you probe smaller distances. Eventually the fluctuations become so strong that they overwhelm any attempt to define a precise location. The Planck length emerges as the scale where these fluctuations reach a critical level, making the idea of a stable position impossible. What ties these explanations together is the idea that the Planck length isn't a property of a particle or a place, but of the universe itself. It arises from the interplay of the most fundamental laws we know, and each approach points toward the same conclusion. Space has a limit to how finely it can be divided, and that limit arises because the rules governing energy, momentum, and gravity interact in a way that prevents infinite subdivision. Even though the Planck length is an incredibly small scale, its existence has consequences for how the universe behaves. For example, some theories suggest that the early universe, when it was extremely hot and dense, may have had a structure influenced by the Planck length. When the universe was young, the distances between events may have been comparable to the Planck scale, meaning the smooth space-time we experience today emerged only after the universe expanded and cooled. This raises the possibility that time itself may have behaved differently near the beginning, with its flow emerging only after the universe grew beyond the smallest scales. Some theories related to quantum gravity try to derive the Planck length by imagining space as being made from networks of connections. In these models, the universe isn't a continuous medium but a collection of linked nodes, and the Planck length is the minimum distance between them. The geometry of the universe emerges from the pattern of connections rather than from a continuous fabric. In these models, the Planck length exists because it represents the spacing between the smallest units that make up space-time. Other theories look at the holographic principle, which suggests that the amount of information stored in a region of space is proportional to the area of its boundary rather than its volume. If this principle is correct, then the Planck length is the size of the smallest unit of area that can store information. In that case, the Planck length exists because it is the basic unit of the universe's information storage. Anything smaller wouldn't have the capacity to encode anything, so the universe draws the line there. Yet another idea stems from string theory, which replaces point-like particles with tiny vibrating strings. In this framework, the Planck length is the characteristic size of these strings. They cannot be compressed into anything smaller because their tension resists such compression. If the length of a string sets the minimum scale of space, then the Planck length exists because strings cannot shrink below that size. This gives a physical interpretation to the boundary, based on the properties of the objects that form the foundation of matter. Even though these explanations come from different directions, they all agree on something important. The Planck length exists because the universe cannot support meaningful structure below that scale. Whether the reason is gravitational collapse, quantum uncertainty, discrete geometry, information limits, or the properties of hypothetical strings, the outcome is the same. Space refuses to allow smaller distances because smaller distances cannot be described consistently by the physical laws we know. It's tempting to think of this as a kind of brick wall, a stop sign that tells physics not to go any further, but that isn't quite accurate. The Planck length isn't a barrier, it's a signpost. It marks the point where the theories we use now lose their reliability. It tells us that new physics must exist beyond that scale, even though we don't yet know what that new physics looks like. The Planck length isn't the end of the story, it's the beginning of a deeper one. If you think of the measurable universe as a map, the Planck length is the point where the edges become fuzzy. The terrain beyond that point hasn't been charted, not because nothing is there, but because the paths leading into it aren't passable with the tools we have. In a sense, the Planck length exists because it represents the place where the universe changes character. Before that scale, space behaves like a flexible, continuous fabric. After that scale, it becomes something different. Understanding why this length exists helps clarify why the universe behaves the way it does at larger scales. It explains why atoms have the sizes they do, why gravitational forces become dominant at large masses, and why the quantum world has limits. It ties together the structure of particles, the behavior of waves, and the geometry of space-time. All of these patterns are linked to the constants that define the Planck scale. Knowing that the Planck length exists is one thing. Understanding why it appears so naturally in the equations that describe the universe suggests something deeper. It hints that the universe has built-in boundaries, not for our benefit, but because these boundaries emerge from the rules themselves. The Planck length is not arbitrary, it's unavoidable, and its existence continues to guide the search for the deeper laws that shape everything from the behavior of electrons to the expansion of galaxies. As we move further toward the smallest scales the universe allows, we end up reaching a point where the familiar ideas we carry about space start slipping away. Most of the time, we treat space almost like a quiet stage, something that just sits there while everything else happens on top of it. Distances feel straightforward, locations feel permanent. Motion feels like a shift between 2 points that always exist. Even when we think about smaller and smaller objects, we keep imagining that the background they sit in remains the same. But when distances shrink toward the Planck length, that background begins to lose its reliability. The smooth, silent stage turns into something far less stable, and eventually the whole idea of space begins to break down. We don't notice this in everyday life because the scales we interact with are enormously larger. Even the movements inside an atom, confusing as they may be, still take place in a structure that behaves like continuous space. There are regions to move through, boundaries to identify, and positions that can be described with reasonable accuracy. Nothing at our scale ever gives us the sense that space could fail in its role as the underlying structure. But our daily experience is shaped entirely by distances that are billions of times larger than those where space begins to lose its meaning. If something behaves reliably at human scales, it's easy to assume it behaves the same way everywhere. But this assumption breaks down long before we reach the Planck length. To understand why, it helps to think about what space does. In physics, space provides a framework for measuring separations. It tells us how far apart 2 points are, what direction one object lies relative to another, and what paths exist between them. When we talk about a location, we imagine space as something smooth that allows us to move in any direction without encountering interruptions. This smoothness is crucial to our sense of how the world works. Cars drive on roads because we assume the geometry supports continuous travel. Light travels in straight lines because space is expected to be uniform unless something bends it. Even the idea of a coordinate system used in every branch of science assumes that space doesn't suddenly shift its behavior from one moment to the next. This smoothness also appears in Einstein's theory of general relativity, which treats space as something that can warp and bend but still remains continuous. That theory describes gravity as the curvature of space and time caused by mass and energy. Even when that curvature becomes extreme, space remains a smooth surface at its core. Einstein's equations rely on derivatives, slopes, and continuous changes. Nothing in his framework allows space to break into pieces or dissolve into something unrecognizable. But as we move deeper into the quantum realm, we discover that continuity becomes harder to defend. Quantum mechanics describes particles and fields that fluctuate constantly, especially at small scales. Energy pops in and out of existence in tiny bursts. Particles appear and vanish. At these scales, motion is no longer smooth. Instead, it becomes a mixture of probabilities. Even so, quantum mechanics still assumes space is the background where all this happens. Space doesn't get a special treatment in the basic quantum equations. It remains a fixed, silent backdrop. The difficulty arises when we try to combine quantum mechanics and general relativity. On their own, both theories work extremely well. But when both effects matter at the same time, the equations start contradicting each other. Gravity, as described by relativity, expects space to be continuous. Quantum mechanics, with its energetic fluctuations, injects disturbances into that space. At large scales, gravity smooths out these disturbances, but as the scale decreases, the disturbances become stronger, and gravity becomes less able to contain them. Eventually, the fluctuations are so strong that space can no longer be treated as a smooth surface. It begins to fold, twist, and react unpredictably to the energy on these small scales. This unstable behavior grows dramatically as you approach the Planck length. Normally, empty space seems quiet, but quantum mechanics says that this quiet appearance is misleading. Even what we call vacuum contains constant activity. Fields fluctuate, particles appear briefly, energy jitters unpredictably. These effects are usually so small that we only notice them indirectly. But as we push downward in scale, the fluctuations increase in intensity. At around the Planck length, they become so strong that space stops being a stable platform. It becomes chaotic. This chaos is sometimes described as quantum foam. It's a term that tries to capture the idea that space at the smaller scales behaves less like a smooth surface and more like something constantly bubbling and shifting. In a normal sense, foam is made of small pockets that appear and disappear. At the Planck scale, the foam isn't made of bubbles of air or water, but temporary distortions of space-time itself. Tiny regions curve inward, then outward, then sideways. You might get short-lived microscopic black holes that form and evaporate. You might get distortions that last for such short periods of time that the idea of duration becomes meaningless. This is the point where space stops behaving like space. At larger scales, space helps define distances. But in this chaotic region, distances stop being well defined. If the geometry changes violently from one moment to the next, how do you define the separation between 2 points? If the curvature shifts faster than anything can respond to it, what does motion even mean? The usual idea of a path becomes blurry, because any path you try to draw would be disrupted almost instantly by quantum fluctuations. It's not just position that becomes unreliable. Time also begins to lose its usual structure. General relativity treats time as part of the same fabric as space, and if that fabric is unstable, then time can't remain stable either. At the Planck scale, intervals of time may become so short that they can't be meaningfully distinguished from one another. Just as distances might disappear into a haze of fluctuating geometry, durations might dissolve into a blur of jittery changes. The familiar flow of time might not exist. Instead, time becomes more like a statistical behavior that only settles into something steady at scales much larger than the Planck time. This breakdown is not random. It follows naturally from the rules of quantum mechanics and gravity. If quantum mechanics insists on constant fluctuations, and gravity insists on responding to energy, then the closer you get to the smaller scales, the more those responses become unmanageable. The equations diverge, values explode, predictions contradict each other. The theories we rely on stop making sense, not because they contain mistakes, but because they aren't designed for this situation. These contradictions reveal something important. The reason space stops behaving like space at these scales isn't that space fails, it's that our current theories fail to describe it. The universe itself doesn't collapse or disappear. It simply enters a regime we don't yet know how to model. The Planck length marks the limit where our current framework no longer applies. Physicists have tried many approaches to create new frameworks that remain consistent below this scale. One popular idea is that space is fundamentally discrete. In this view, the smoothness of space at larger scales is an illusion, emerging from many tiny units stitched together in a network. If each unit has a minimum size, then the Planck length would be the spacing between them. At small scales, the smoothness breaks down because you can't divide these units any further. It's like zooming into a digital photograph. From far away it looks smooth, but as you zoom in, you start seeing the individual pixels. The Planck length would be the size of the pixel in this analogy. Another idea suggests that space is woven from loops or discrete structures that create a measurable geometry only at larger scales. At the Planck scale, the loops overlap and fluctuate, and geometry becomes undefined. This would explain why you can't identify distances or directions with clarity. The structure responsible for those distances simply doesn't exist in a stable form. Some approaches go further and suggest that space-time is not fundamental at all. Instead, it emerges from relationships between physical systems. In that case, space isn't a thing, but a pattern that arises when enough degrees of freedom interact. At extremely small scales, that pattern might fall apart, the same way that temperature doesn't exist for a single molecule. A single molecule has energy, but it doesn't have a temperature. Temperature emerges only when many molecules interact. Similarly, space might not exist in the same way for isolated or extremely small systems. Other theories look at information. They propose that the universe is limited in how much information it can store within a given region. The Planck length might represent the smallest region capable of holding a meaningful amount of information. Concepts like position or direction might require a minimum amount of information to be defined. If you go smaller than the Planck scale, there isn't enough capacity to encode those quantities. The breakdown of space would then be a matter of insufficient information, not physical instability. Whatever the explanation turns out to be, they all share an outcome. The neat, continuous, predictable space we're used to cannot survive down to arbitrarily small distances. The rules that give space its character at human scales depend on features that simply don't apply when you get too close to the Planck length. The stability, the smoothness, the continuity. All of these traits emerge from the behavior of larger scales. They are not inherent qualities of space at every level. This doesn't mean the universe becomes chaotic or meaningless at microscopic levels. It means that the universe has layers, and the layer we interact with behaves differently from the one that sits beneath it. The transition between these layers is gradual at first, then sudden as you approach the smallest scales. Once you cross that boundary, the familiar concepts break down. Even though space stops behaving like space at the Planck scale, this doesn't make the universe inaccessible. Instead, it encourages new forms of thinking. It hints that deeper structures exist that might explain how space rebuilds itself into something stable at larger scales. It motivates theories that aim to unify quantum mechanics and gravity, and it shapes our understanding of black holes, early cosmology, and the deepest properties of matter. What makes this exploration calming in its own way is the sense that even when the world becomes unfamiliar at its foundations, it still follows rules. The uncertainty isn't a sign of disorder, it's a sign that the universe is richer than our current descriptions. Up to a certain point, even the smallest things still feel arranged in some kind of order. Atoms have orbitals, electrons occupy energy levels, Quarks sit inside protons and neutrons. Fields occupy space in a stable pattern. But when the distances shrink toward the Planck length, the idea of order becomes difficult to maintain. The world stops presenting itself as a set of coordinated pieces and starts behaving more like a restless surface, agitated in ways that don't resemble anything we can see or touch on larger scales. This restless environment is sometimes called quantum foam, a term that hints at movement, fluctuations, and constant change at the foundation of reality. To understand why this kind of behavior appears, it helps to remember that quantum mechanics insists that empty space is not truly empty. Even the most perfect vacuum, stripped of all particles, all photons, all matter and radiation, still contains energy that fluctuates. These fluctuations arise because the uncertainty principle forbids any region of space from having exactly zero energy. If it did, the energy level and the duration of that state would both be known precisely, which the uncertainty principle doesn't allow. So the vacuum always carries some jitter, some minimal activity that never quite settles down. This activity is usually tiny and barely noticeable, but at extremely small scales it becomes more intense. Imagine trying to observe an extremely small region of space. The smaller the region you isolate, the larger the uncertainty in the energy inside it. That increasing uncertainty makes the fluctuations more severe, and when you try to focus on a volume of space near the Planck length, the fluctuations become so large that the energy inside that region is enough to warp space-time dramatically. This is why people talk about quantum foam. It's not a literal liquid or a frothy substance, but a way of describing how space becomes unstable at tremendously small scales. Regions of high energy forms suddenly distort the geometry and then vanish. The geometry flips between different configurations so quickly that no stable shape exists. What makes this behavior especially interesting is that it appears even when you're not trying to disturb the region at all. In quantum mechanics, fluctuations are not caused by interference or by measurement. They happen naturally because of the rules that govern energy and momentum. The vacuum is full of these fluctuations at all scales, but they only dominate when the scales become small enough. At larger distances, the fluctuations average out, and the vacuum looks smooth. At smaller distances, the fluctuations swamp everything else. They begin to define the environment rather than serve as small corrections. This idea leads to an unusual picture of what the universe might look like at these tiny scales. Instead of seeing space as a stable backdrop, we see it as something like a constantly shifting landscape. One moment a region might have a tiny curvature resembling a dip. The next moment it might resemble a spike. Sometimes tiny black hole-like objects form briefly, then evaporate through quantum processes that happen in a fraction of a second. These objects are sometimes called virtual black holes. They're not the same as large black holes formed by stars collapsing, but they share similar features on a much smaller scale. They appear because the energy fluctuations in such a small region become large enough to create temporary curvature so intense that it resembles a microscopic event horizon. This constant formation and evaporation create a dynamic environment that doesn't settle into any stable pattern. The geometry is unpredictable. The direction or distance between 2 points may shift so rapidly that it loses meaning. If you tried to place a marker or a reference point in this environment, it wouldn't stay fixed long enough to provide reliable information. It would be like trying to mark a spot on the surface of water that is boiling violently underneath. The surface itself is never still enough to anchor anything. This turbulent environment is not something we can observe directly. None of our tools can reach these scales, but the mathematics of quantum field theory and general relativity both point toward this outcome. When the quantum fluctuations of the vacuum are combined with the curvature of space-time, the predictions show that space becomes irregular. These predictions are not wild guesses. They emerge naturally from equations that have been tested thoroughly at larger scales. The issue is not that the equations are wrong, but that they don't behave well when pushed to the extremes. They produce infinities, contradictions, or conditions that no longer describe a smooth geometric surface. One important point is that quantum foam doesn't mean space is full of particles bouncing around. The fluctuations are not like a swarm of physical objects. Instead, they are temporary disturbances in energy that affect fields and curvature. These fluctuations do not have durable existence. They come and go so quickly that they cannot be used to form stable structures. They don't propagate outward. They don't create lasting effects unless they interact with something else. But the fact that they occur at all means that space is not a rigid framework. It responds continuously to these fluctuations. This responsiveness removes the idea that space is empty. The vacuum becomes something like a restless medium with constant activity. That doesn't mean it's a substance. It doesn't have texture or weight in the usual sense. But it isn't passive either. The vacuum of quantum field theory is a dynamic environment, and quantum foam represents the limit where that dynamism becomes dominant. It's the point where fluctuations take over and the smoothness of space collapses under their influence. In some ways, quantum foam can be viewed as a sign that our current theories are incomplete. The equations of general relativity predict smooth curvature, but they were not designed to handle the rapid fluctuations introduced by quantum mechanics. Quantum mechanics describes fluctuations but assumes space is stable. The foam is what happens when you try to apply both theories at once without a framework that unifies them. The result is uncontrolled behavior that neither theory fully explains on its own. This is one of the motivations behind the search for a theory of quantum gravity, a theory that would describe space in a way that can handle these fluctuations without producing contradictions. Different theories of quantum gravity attempt to explain the foam in different ways. Some of them say the foam is a real feature of space. Others say it represents the failure of our current tools and that space might be made of something more fundamental that is not captured by either quantum mechanics or general relativity. For example, in loop-based approaches, space is thought to consist of small units linked together. In that view, quantum foam arises because on small scales, the links fluctuate in strength or orientation. The geometry changes because the connections change. The foam is the visible effect of deeper discrete structures rearranging themselves constantly. In other approaches, such as string-based models, the foam arises from the vibrations of tiny strings or membranes. The geometry of space is influenced by the vibrational states, and at very small scales the vibrations become too energetic to settle. That leads to a jittery environment that looks like foam. The foam in this case is a sign of high-energy interactions of the tiny fundamental objects that underlie particles and fields. In theories that treat space-time as emergent rather than fundamental, the foam might not be a physical structure at all. It might be a sign that the deeper processes haven't combined enough degrees of freedom to produce stable space-time. In these models, space-time is like a pattern that appears when many smaller elements interact. At the Planck scale, the interactions might not be numerous enough to produce a smooth structure, resulting in something that looks like foam before the stable pattern emerges. In approaches based on information, the foam could reflect the limits of how much information can be stored in a small region. If the universe has a lower bound on the amount of information needed to define geometry, then regions smaller than the Planck length might not have enough information to form a consistent geometry. Instead, the geometry flickers between possible states. That flickering looks like foam, but the foam isn't a physical thing. It's the visible result of information limits at small scales. Despite these differences, all these perspectives agree on a central point. The foam marks a regime where space-time becomes unstable and the familiar concepts break down. It represents the mismatch between theories that work well in isolation but fail when combined at extreme conditions. The foam is not the end of our understanding, but the beginning of a direction that leads deeper into the search for what space-time really is. It's worth noting that even though quantum foam sounds chaotic, it doesn't directly affect most physical processes at larger scales. The fluctuations are so small and so fast that they average out into a stable structure. In fact, the stability we see at normal scales is impressive, considering the constant activity underneath. It's similar to how large bodies of water appear flat and calm, even though the molecules inside them are moving chaotically. The foam is hidden beneath the smoothed-out geometry that emerges at larger scales and only becomes relevant when distances approach the Planck length. The foam might also play a role in phenomena like black hole evaporation, where quantum effects near extremely small horizons become significant. But even in these extreme environments, the foam remains buried under layers of larger-scale geometry. It's only when we insist on probing deeper that we reach the point where the foam matters. This deep, unstable region is difficult to imagine. It doesn't behave like anything we experience. There are no fixed shapes, no predictable distances, no steady flows of time. Instead, it is a place where events happen almost too quickly to describe, where geometry is created and erased constantly, and where the familiar categories of physics start to blend together. Despite how unfamiliar it sounds, there is something calming in recognizing that the universe has a foundation that rests not on stillness, but on constant motion. Even the most stable structures emerge from deeper processes that never stop fluctuating. The foam beneath reality reminds us that change is not an exception, but a built-in quality of the world. Stability rests on constant activity, and large-scale order grows from underlying fluctuations that never fully rest. If space stops behaving like a smooth background at incredibly tiny distances, and if the quantum foam churns so actively that geometry cannot settle into a fixed shape, then it becomes natural to wonder whether there is something beneath that turbulence giving rise to all of it. Something that sits deeper than the fluctuations, not as a rigid structure, but as a kind of minimal ingredient from which space-time emerges. This leads to the possibility that space itself may not be continuous. Instead, it might be made of grains, the way a photograph is made of tiny dots, or a computer screen is made of pixels. These grains wouldn't be physical objects sitting in a medium. They would be the smallest units of space-time itself, flickering in and out as they organize the larger geometry we experience. This idea doesn't come from imagination alone. It grows out of the realization that our familiar concepts struggle at small scales. Every attempt to push the definition of a distance below the Planck length breaks the consistency of the theories we rely on. The geometry becomes unstable. The measurements become impossible. The idea of a location loses meaning. It's as if the universe refuses to let distances shrink any further in a continuous way. That refusal can be interpreted as a hint. Perhaps the universe has no continuous structure at those scales. Perhaps instead it consists of discrete units that cannot be subdivided. To picture this, it helps to think about something more familiar, like film or printed photographs. When you stand far enough away from a photograph, it looks like a smooth image with contours, shading and detail. But if you move closer and examine it under magnification, what looked smooth becomes a pattern of small dots. At a normal viewing distance, the dots blend together into shapes, but the closer you get, the more obvious the dots become. If you continue zooming in, eventually the picture breaks apart into its smallest components. The image no longer looks like a picture at all. It looks like a field of separate marks with no intermediate values. If space-time behaves in a similar way, then what we think of as smooth geometry at everyday scales may actually be built from a dense network of tiny, discrete elements. Each element would be so small that under normal conditions they blend seamlessly. Only at the Planck scale would the discreteness become visible. The flickering that shows up at extremely tiny distances could be a sign that the grains are constantly changing orientation or connection, causing geometry to reconfigure itself. Nothing in this picture suggests that the grains are objects floating in some background medium. They wouldn't exist inside space. They would be space. Each grain would hold a small amount of information about connections or distances, and the way the grains link together would define the geometry. Instead of space being a continuous fabric, it would be a network made from many small units. The fluctuations that appear at tiny scales would be the result of constant rearrangement in this network. Different theories propose different shapes or structures for these grains. Some treat them as loops that link into a web. Others treat them as small nodes connected by edges. In some models, the grains have areas or volumes associated with them. In others, they represent relationships rather than dimensions. What these models agree on is that space-time emerges from these underlying units only when enough of them combine. It's the collective behavior of the grains that produces geometry at large scales. At human scales, the grains would be far too small to detect. The distances between them would be many orders of magnitude below anything we can probe. Even particle accelerators that smash protons together with enormous energy cannot reach those scales. This means the geometry we experience is like a blurred image, smoothed out because we cannot resolve the individual components. But the smoothing is not a flaw. It's what allows geometry to function at all. Stable shapes, distances, and directions emerge from the average behavior of countless microscopic elements. The flickering we attribute to quantum foam could arise because the grains themselves are not fixed. Their connections might change rapidly. The values they hold might fluctuate. At extremely small scales, the structure they form could shift faster than any stable geometry can emerge. At larger scales, the fluctuations would average out, creating something steady. This is similar to how the motion of molecules in air is chaotic and unpredictable. Yet the air itself behaves in a stable and predictable way at everyday scales. The chaos at the molecular level does not prevent the air from having pressure, temperature, and flow. Those stable features emerge from the average of countless tiny interactions. If space-time is composed of grains, then many of the strange behaviors predicted near the Planck length start to make more sense. For example, the idea that distances become uncertain no longer represents a failure of space. It represents a limit imposed by the resolution of space-time. When the distance between 2 points is only a few grains wide, the number of grains involved might fluctuate, or the connections might shift, causing the distance to vary slightly. The fluctuations wouldn't be noise in a system. They would be the natural behavior of a structure made of discrete elements. This kind of interpretation can explain why the quantum fluctuations of the vacuum become dominant at small scales. If space is discrete, then the fields defined on that space must adjust to the irregularities in the underlying structure. The vacuum fluctuations might be a sign that fields cannot settle into a stable configuration because the geometry keeps changing at tiny intervals. At larger scales, the flickering becomes less noticeable because the fields average out over many grains. But at the Planck scale, the flickering would dominate everything. Some theories propose that the grains carry information about area or volume. For example, each unit might represent a smallest possible area that cannot be divided further. That would mean that surfaces, not just distances, become discrete. In these models, the area of a surface is calculated by counting the number of grains on it. This would place the Planck area as a fundamental unit of geometry. Similarly, volumes could be derived from the three-dimensional arrangement of grains. This would also imply that space-time itself has a finite information capacity. A region of space could only contain a certain number of grains, and therefore a certain amount of information. This idea links to the holographic principle, which suggests that the information content of a region is proportional to its surface area rather than its volume. If the grains that support space-time are associated with area, then the holographic principle might emerge naturally from this discrete structure. This would mean that the flickering grains do more than shape geometry. They also shape how information is stored in the universe. The boundaries of regions could determine information content because the grains accumulate along surfaces. String-based theories offer another perspective. Instead of grains or loops, space-time might be made of tiny vibrating strings. These strings have a minimum length associated with them, and that length is on the order of the Planck scale. The flickering of space-time could arise from the vibrations of these strings. When the wavelength of a vibration becomes too short, the energy increases dramatically, preventing the string from being compressed further. That resistance imposes a natural lower bound on distances, effectively turning the Planck length into the size of the smallest physical structure. The flickering would then represent the different vibrational states interacting with each other. Some approaches consider that the grains might not have shapes at all. Instead, they might represent relationships between underlying degrees of freedom. In such models, geometry arises when these relationships form patterns. At small scales, the relationships change constantly, so no stable pattern forms. But as you move to larger scales, the relationships become more statistically stable, producing a geometry that appears smooth. This is similar to how certain patterns arise in large groups of interacting elements, even when individual interactions are unpredictable. One of the simplest arguments for space-time grains comes from information theory. If the universe has a finite amount of information in any region, then there must be a smallest unit of space that can hold that information. You cannot store infinite information in a finite region. This leads naturally to the idea that space is made of discrete units. Otherwise, distances could be divided indefinitely, and the information content would be limitless. The Planck length then appears as the smallest unit of meaningful geometry. Another reason to consider grains is the behavior of entropy near black hole horizons. Calculations show that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This suggests that the surface area is made of discrete units. If each unit of area corresponds to one grain of space-time, then the entropy becomes a count of how many grains fit on the surface. This connects the Planck area with the fundamental building blocks of space-time. The flickering of these grains could be what produces the quantum behavior of black holes. In all these interpretations, the flickering grains are not objects in the traditional sense. They are not made of matter or energy in the way particles are. They don't have mass or charge, they don't move through space. Instead, they are the components of space. They define distances and directions by their connections and interactions. When those connections change, the geometry changes. This is why geometry becomes unstable at small scales. The grains don't hold fixed positions. They rearrange rapidly. The flickering is the universe reorganizing itself at its smallest levels. Even though this picture sounds unusual, it offers a consistent way to think about why space behaves smoothly at large scales and chaotically at small ones. It suggests that the stability we rely on comes from the cooperative behavior of enormous numbers of grains. Just as a fabric looks smooth when you don't see the individual fibers, space-time looks smooth because the grains blend together. But when you try to examine a piece of fabric under extreme magnification, the fibers become visible and the fabric stops looking continuous. The same idea applies here. The flickering occurs because the magnification becomes extreme. This view also fits with the idea that space-time is not static. Even at large scales, space-time changes in response to mass and energy. Gravity curves it, expansion stretches it, waves ripple through it. These large-scale behaviors could arise from collective changes in the grains. When the grains shift in certain patterns, the curvature changes. When they shift in other patterns, waves propagate. This would mean that gravity and the geometry of space-time arise from the behavior of the grains. What makes this satisfying is that it ties together many different observations. It explains why distances cannot be meaningfully defined below the Planck length. It explains why geometry becomes unstable at those scales. It explains why information appears limited by areas. And it offers a framework in which the familiar equations of general relativity emerge as approximations of deeper structures. The flickering is not noise. It's the fundamental activity that builds the stable environment we see. Even though no direct experiment has revealed the grains, their existence would explain the limitations we encounter. And whether space-time ultimately turns out to be discrete, emergent, or something else entirely, the idea of grains provides a valuable framework for understanding why the Planck length acts as a boundary, and why space behaves so differently near that boundary. We eventually reach a point where gravity, normally the slowest and most patient of all forces, begins to behave in a way that's anything but gentle. For most of the scales we experience, Gravity is the least dramatic influence in our lives. It's steady, reliable, and rarely surprising. It keeps us anchored to the ground. It shapes the orbits of planets. It governs the motion of stars and galaxies. Even when it acts on enormous scales, its influence changes in smooth, predictable ways. You can leave a coffee mug on a table and trust that gravity won't suddenly shove it sideways or pull it upward. You can walk or sit or rest without wondering whether gravity will flicker or reverse direction. It's consistent at human scales. It's consistent across continents. It's consistent across the solar system. But this comfortable steadiness depends entirely on the fact that gravity, in general relativity's description, responds to mass and energy in a calm, continuous way. Mass bends space-time. Energy curves space-time. But as long as the masses and energies aren't extreme and as long as the scales are large, space-time remains a smooth surface. Gravity behaves like a precise but patient sculptor, shaping the geometry into forms we can navigate and predict without trouble. At small scales, however, gravity begins to lose that patience. The smooth curvature that general relativity relies on becomes overwhelmed by the violent fluctuations that quantum mechanics produces. Normally, these fluctuations don't affect gravity much at all. Even the jitter of quantum fields in ordinary situations barely registers in the curvature of space. The energy involved is tiny compared to the amount needed to create noticeable gravitational effects. Gravity is weak at everyday scales. It's weak even at the scale of atoms. Compared to the electromagnetic force or the strong nuclear force, gravity might as well be a distant whisper. But weakness isn't permanent. As distances shrink, the energy density inside those regions rises dramatically due to quantum uncertainty. And gravity doesn't care that the total energy is small. It cares about how concentrated that energy is. If you squeeze even a small amount of energy into a tiny enough region, the gravitational response grows more severe. This is the part that becomes important at the Planck length. The smaller the scale, the more violently energy fluctuates, and the more violently gravity reacts. At extremely tiny distances, far smaller than any particle we can measure, the vacuum energy can spike so suddenly and so strongly that space-time briefly curves inward as if a microscopic object with enormous density had appeared. This curvature looks something like a miniature black hole, though it exists only for a fleeting moment before the fluctuation that created it vanishes and the geometry rebounds. That's one of the reasons people imagine the tiniest parts of the universe as bubbling, unstable regions. The curvature doesn't settle. It doesn't form a smooth surface. It reacts to bursts of energy that appear and disappear constantly. In ordinary situations, general relativity treats gravity as a smooth field described by elegant equations. But the moment you try to apply those equations to extremely small scales, the math becomes unstable. The curvature terms grow uncontrollably. The predictions become inconsistent. Gravity, which normally keeps everything in a reliable pattern, becomes unruly. It distorts and twists so dramatically that the geometric picture of space-time no longer makes sense. At a certain point, the equations stop yielding meaningful values altogether. This unruliness isn't a sign that something is wrong with gravity. Instead, it's a sign that the theory we use to describe gravity wasn't designed for such intense conditions. General relativity was built for planets, stars, and galaxies. It handles everything from falling apples to black holes fairly well, but it was never meant to handle regions where the fluctuations of energy reach Planck scale intensities. At those scales, the underlying assumptions of the theory, that spacetime can be treated as smooth and continuous, no longer hold. The smooth surface becomes a flickering landscape. The curvature becomes too extreme to model with ordinary equations. Quantum mechanics also wasn't designed for these scales. It assumes that spacetime is a stable stage on which particles and fields behave according to probabilistic rules. But that assumption breaks down when the stage itself begins to jitter wildly. If the geometry changes faster than the quantum fields can respond, then the foundational equations of quantum mechanics become unreliable. They need space-time to have a stable structure, at least locally. But near the Planck scale, no such stability exists. This creates a situation where both theories break down simultaneously. Quantum mechanics cannot predict the behavior of fields in a fluctuating space-time, and general relativity cannot describe the curvature produced by those fields. Gravity becomes large when quantum mechanics becomes active, and quantum mechanics becomes chaotic when gravity becomes large. The two frameworks collide. The collisions appear in the equations as infinities or contradictory predictions. These mathematical breakdowns reflect a deeper physical issue. The rules we use simply don't apply when the curvature becomes violent and the energy fluctuates rapidly. To grasp why gravity becomes so active at tiny scales, it helps to think about energy concentration. At macroscopic scales, energy is spread out. Even if you compress something like air or water, you cannot concentrate enough energy into a small enough region to significantly warp space-time. But at tiny scales, the energy fluctuations caused by the uncertainty principle create momentary concentrations far greater than anything we encounter at large scales. These fluctuations can't be ignored. When the region under consideration is extremely small, the amount of energy packed into it becomes significant. Even though the total energy of the universe at any given moment remains finite, local fluctuations can spike so sharply that the curvature changes dramatically. This is where the behavior of gravity becomes tricky. The gravitational effect of a fluctuation grows rapidly as the region shrinks. If the region becomes small enough, the gravitational influence becomes strong enough to trap the fluctuation, collapsing it into a tiny horizon before it evaporates. These horizons are not black holes in the traditional sense. They are brief geometric disturbances that appear because the energy momentarily meets the conditions for intense curvature. They are unstable and vanish quickly, but their existence shows that gravity cannot remain quiet at small scales. This effect also reveals why distances smaller than the Planck length cannot be meaningfully defined. If the region you're trying to measure collapses under its own energy fluctuations before you can measure it, the idea of distance breaks down. You can't identify 2 points in a region that collapses instantly or fluctuates violently. You can't probe a geometry that doesn't remain consistent long enough for a measurement to be made. The boundary is not technological. It is physical. The very act of trying to define a distance below the Planck length triggers gravitational responses strong enough to erase the geometry you are trying to study. Different approaches to quantum gravity try to interpret this behavior in different ways. Some treat the violent curvature as evidence that space-time must be discrete. In these models, gravity's unruliness reflects the fact that the continuum picture fails. The flickering curvature becomes the signature of underlying units that general relativity smooths over at larger scales. When the smoothing breaks down, the discreteness reveals itself in the form of unpredictable curvature. Other approaches suggest that gravity's intensity at small scales hints that gravity might be emergent. In these models, gravity is not a fundamental interaction, but arises from deeper thermodynamic or informational principles. If gravity emerges from statistical behavior, then at very small scales the statistics no longer produce a stable field. The irregularities that appear would be expected because the behavior of small numbers of microscopic components is often unpredictable. Gravity becomes unruly because the emergence mechanism fails when there aren't enough components to produce smooth effects. Another group of theories interprets gravity's behavior as a sign that space-time must arise from networks or graphs that encode relationships between microscopic degrees of freedom. In these models, geometry appears only at large scales. At tiny scales, the networks rearrange themselves constantly, causing the curvature to fluctuate. Gravity becomes intense not because a mysterious new force appears, but because the network structure cannot stabilize into a smooth geometry at those scales. Regardless of the interpretation, All of these approaches agree that gravity and quantum mechanics must be combined into a single framework to describe what happens at the Planck scale. The unruly behaviour of gravity is not a flaw, it's a clue. It tells us that neither theory on its own is enough to describe the full story. The intense curvature is the point where the universe reveals the incompleteness of our current models. What makes this even more interesting is that the same unruliness appears in discussions of the early universe. At the very beginning, distances might have been close to the Planck scale. The curvature of space-time might have been extreme. The fluctuations of quantum fields might have been dominant. If that was the case, then the universe we experience grew out of a phase where gravity behaved in exactly this kind of chaotic way. The smooth space-time we see today might be the large-scale result of a violent and unstable phase that smoothed out as the universe expanded. This possibility offers a different perspective on the horizon of the Planck length. Instead of being a barrier or a wall, it might be the same kind of boundary we see when we study phase transitions. A cup of water looks smooth until you reach the molecular scale where it becomes chaotic. A metal bar looks solid until you zoom in far enough to see atoms vibrating in all directions. Many substances have dramatically different behaviour in their microscopic forms compared to their macroscopic appearance. The Planck length might mark the scale where space-time transitions from a grainy, flickering state to a smooth one. If that's true, then gravity's unruly behaviour is a sign of transition rather than failure. It's the signature of space-time responding to its microscopic structure. It's the place where gravity stops being a gentle curve and instead becomes the dynamic rearrangement of whatever underlying components exist. The geometry isn't breaking, it's shifting between behaviours depending on scale. Even though we can't observe this directly, the existence of this region helps guide theoretical work. Any theory that hopes to describe the true nature of space-time must explain gravity's behaviour at small scales and reproduce the smooth behaviour at large ones. The transition between the two must be natural and consistent. The unruly behaviour becomes a test. A theory must be able to describe it without producing contradictions or infinities. What's calming, even in this turbulent picture, is the sense that the universe doesn't lose its coherence at these scales. The overwhelming intensity of curvature doesn't signal chaos in the way we usually think of chaos. It signals the limitations of our models. The universe doesn't stop functioning. Our descriptions do. That's a reminder that the world often remains structured even when our tools can't capture it. The small-scale unruliness doesn't contradict the large-scale stability. Instead, it complements it. The complexity at small scales gives rise to simplicity at larger ones. As we continue moving deeper into the smaller scales the universe permits, there comes a point when the discussion naturally turns toward the constants that shape these boundaries. They may seem like simple numbers on paper, the kind you might gloss over in an equation, but they are far more than that. They are woven into everything the universe allows and everything it refuses to allow. They appear in every model we've built, from the everyday physics that describes falling objects to the theories that attempt to explain the birth of the universe itself, and without them, there would be no way to speak about the Planck length, the Planck time, or the Planck mass. These constants form a kind of strange marriage, a partnership that defines the smallest meaningful distance, the smallest meaningful interval, and the smallest meaningful energy scale. To appreciate what this marriage means, it helps to think for a moment about what a constant really is. When we talk about physical constants, we are referring to quantities that never change. The speed of light in a vacuum is the same everywhere in the universe. Planck's constant has the same value in every lab, on every planet, in every galaxy, at every moment we can observe. Newton's gravitational constant affects the motion of stars, planets, atoms, and galaxies without variation. These constants aren't like measurements that might shift slightly depending on how you take them. They're the rules that define how everything behaves. If any of them were different, even by a small fraction, the universe as we know it would be completely unrecognizable. It's easy to take these constants for granted because we learn about them in isolated contexts. In one setting, the speed of light appears as a limit for motion. In another, Planck's constant appears in discussions of photons or energy quantization. In another, Newton's constant appears in the equations describing gravity. But when these constants come together, as they do in discussions of the Planck scale, they produce something new, something none of them produce alone. Their combination gives rise to fundamental limits. These limits don't come from any specific physical object or measurement. They emerge from the relationships between the constants themselves. The speed of light is one of the most familiar constants. It sets the highest speed at which information or matter can travel. But it also sets the scale for how space-time behaves. It is not simply the speed at which light moves, it's the speed at which causality operates. Distance and time are tied together through this constant. If the speed of light were different, the structure of space-time would be different. The speed of light turns space and time into a unified framework where motion and duration become connected. Planck's constant, on the other hand, defines the scale of quantum behavior. It tells us that energy is not continuous. It comes in discrete amounts. It tells us that particles have wave-like properties. It sets the limit for how precisely we can measure certain pairs of properties. Without Planck's constant, the quantum world would collapse into a classical one, eliminating uncertainty, quantization, and the entire structure of matter as we know it. Atoms wouldn't exist. Electrons wouldn't settle into stable orbitals. Chemistry wouldn't function. Everything made of matter would fail. Then there is Newton's gravitational constant, which determines the strength of gravity. It tells us how masses influence one another, how stars form, how planets orbit, and how galaxies evolve. Without this constant, gravity could be too weak to form stars or too strong for stable planetary systems. It shapes the large-scale structure of the universe, determining everything from the motion of moons to the behavior of black holes. When you combine these three constants in a specific way, a new set of scales emerges. These are the Planck scales. They represent the point where the quantum world and the gravitational world meet in such a way that neither theory can stand alone. These scales are not chosen arbitrarily. They arise directly from the values of the constants. You can see it as a kind of mathematical inevitability. The constants themselves define certain fundamental boundaries, and the Planck length is one of them. The Planck length is created by combining Newton's constant, Planck's constant, and the speed of light. Each of these constants contributes something essential. The speed of light relates space to time. Planck's constant relates energy to frequency. Newton's constant relates mass to the curvature of space-time. When you combine them, you obtain a length so small that it sets the boundary where gravity and quantum mechanics become equally important. The Planck length doesn't arise because the universe contains objects of that size. It arises because the constants governing the universe imply that no meaning can be assigned to distances smaller than that. This is part of what makes the Planck length such an elegant concept. It is not tied to any particle or structure. It is not something that exists physically. Instead, it emerges from the interplay of constants that govern all physical processes. When the equations that describe fields, forces, and geometry become incompatible at a certain scale, the constants point to the Planck length as the place where the current picture breaks down. Something similar happens with the Planck time, which is the time it takes light to travel one Planck length. It is an incredibly short interval, so short that it is almost impossible to describe in everyday language. It is not just the smallest time interval that we can imagine. It's the smallest time interval that makes physical sense according to the constants that define the universe. If you try to divide time into pieces smaller than the Planck time, the resulting segments lose meaning because they cannot be associated with physical processes that fit within them. The marriage of constants defines the minimal grain of time in a way that mirrors how it defines the minimal grain of space. The Planck mass also comes from the combination of these constants. It represents the mass at which gravitational effects become as strong as quantum effects. When a particle has a mass near the Planck mass, the gravitational influence becomes too strong to treat separately from the quantum behaviour. This mass is far heavier than any particle we've ever observed. No known particle approaches it. But it tells us something important. It tells us that there is a mass scale at which the structure of space-time must shift. If a particle with the Planck mass existed, it would be heavy enough that its own gravitational influence would collapse its location into a tiny region near the Planck scale. This idea shows how deeply the constants interact. Planck's constant sets the scale for quantum events. Newton's constant sets the scale for gravitational curvature. The speed of light sets the scale for how information moves. Put them together, and you discover the scale where gravity, quantum mechanics, and space-time are inseparable. This scale is not something you can measure with a ruler or detect with a microscope. It is defined by the constants that govern all behaviour. One of the interesting consequences of the marriage between these constants is that the Planck length does not depend on the details of any specific particle or force. It doesn't depend on the mass of the proton or the charge of the electron. It doesn't depend on the properties of quarks, photons, or neutrinos. It depends only on the most general constants. This makes it a universal limit, something that applies to all regions of the universe, regardless of what particles exist there. If the universe had been filled with different particles, or if the laws governing matter had been different, the Planck length would still arise as long as the speed of light, Planck's constant and Newton's constant, existed. To understand why these constants combine the way they do, it helps to think about what each one controls. The speed of light defines the connection between space and time. Planck's constant defines the connection between energy and frequency. Newton's constant defines the connection between mass and curvature. When you combine these relationships, you create a structure where space, time, energy, and curvature are tied together. At large scales, these relationships are smooth. At small scales, they collide. The Planck length is the point where the collisions become unavoidable. If the speed of light were different, the Planck length would be different. If Planck's constant were different, the Planck length would be different. If Newton's constant were different, the Planck length would be different. But the universe gives us the values it gives us, and so the Planck length emerges as a natural boundary, not something imposed by theory, but something dictated by the constants themselves. This brings up an interesting question. Why do these constants have the values they do? Why is the speed of light the speed it is? Why is Planck's constant the size it is? Why is Newton's constant as weak as it is compared to the other forces? These questions don't have clear answers. We know the consequences of the constants. We can describe how they shape the universe, but we don't know why they take the specific values that they do. Some theories suggest that the universe might be one of many possible universes, each with different constants. Others suggest that the constants might arise from deeper relationships that we haven't discovered yet. Regardless of why the constants have their values, the fact that they combine to produce the Planck scale is one of the strongest hints we have about the structure of space-time. It suggests that the universe is organized in a way that forces quantum mechanics and gravity to meet. The interplay between the constants creates a natural boundary between the scales, where quantum mechanics dominates, and the scales where gravity dominates. The Planck length is not a point where something ends. It is a point where two very different regimes overlap so strongly that neither can be understood alone. The strange marriage of constants also guides the development of theories that attempt to unify gravity with quantum mechanics. Any theory that hopes to describe the Planck scale must reproduce the relationships that these constants encode. It must explain why the Planck length, Planck time, and Planck mass arise naturally. It must show how the physics transitions from smooth curvature at large scales to flickering geometry at small scales. It must explain how energy fluctuations interact with curvature, and it must show how geometry emerges from whatever underlying structure exists. This marriage becomes a kind of test for any new theory. If a theory cannot reproduce the Planck scales, it cannot explain the boundary between gravity and quantum mechanics. If it cannot explain the strange behavior at those scales, it cannot fully describe spacetime. The constants act as anchors. They ensure that any acceptable theory respects the structure of the universe as defined by these fundamental numbers. Even though this discussion deals with small scales, there is something calming in recognizing how much stability the constants bring to the universe. They are the reasons atoms exist. They are the reasons stars form. They are the reasons light behaves the way it does. They are the reasons we can define distances and durations. They are the reasons the universe evolves in a predictable way over billions of years. The constants create the structure that allows motion, interaction, and change. They hold the universe together not through force, but through consistency. For most of the universe, and for almost everything we interact with, relativity works beautifully. It captures the way planets orbit, how clocks tick at different speeds in different gravitational fields, how light bends around stars, and even how the universe expands. It describes motion, time, curvature, and gravity with an elegance that still surprises people who work with it. The equations that Einstein wrote down remain some of the most accurate descriptions ever created. When you use them at the scales they were designed for, they work every time. But relativity is built on assumptions that seem completely reasonable when you live in a world of planets and stars. One assumption is that space-time is smooth. Another is that distances can be made arbitrarily small. A third is that the curvature of space-time, no matter how extreme, continues to change in a continuous way. These ideas are so natural that most people never question them. Even when curvature becomes strong near black holes, relativity still treats space-time as a continuous medium. The geometry might be stretched or squeezed, but it never flickers, cracks, or breaks apart. As we approach the Planck scale, however, those comforting assumptions stop working. The equations of relativity begin producing numbers that make no sense. Some values shoot to infinity. Others break apart into contradictions. Distances that should be definable suddenly become uncertain. Curvature becomes too violent to fit inside a smooth mathematical surface. The entire geometric picture begins to wobble under pressures it was never built to withstand. It's as though relativity works perfectly on the upper floors of the building, but can't describe the foundations. The reason for this lies in the nature of the quantum world. Quantum mechanics doesn't treat fields or energies as smooth. It treats them as quantities that fluctuate endlessly. Even the vacuum is full of activity. Events happen spontaneously. Energies spike and vanish. Particles appear and disappear. At large scales, these fluctuations are small and harmless. They barely affect the geometry of space-time. But as you zoom in deeper, the fluctuations grow in intensity. When the scale approaches the Planck length, the fluctuations become so large that the curvature of space-time can no longer remain stable. Relativity simply cannot handle an environment where the geometry changes faster than its own equations can describe. This is the point where relativity begins to break, not because the universe stops working, but because relativity reaches the end of its useful range. The theory doesn't fail due to internal errors. It fails because it was never meant to describe regions where energy oscillates violently and geometry flickers instead of bending smoothly. Just as Newtonian physics stops working when speeds approach the speed of light, relativity stops working when distances approach the Planck scale. Quantum mechanics, on the other hand, thrives in environments where uncertainty and fluctuation dominate. It was built to handle situations where position and momentum cannot be known precisely, or where particles behave both like waves and objects. It predicts probabilities instead of definite outcomes. It doesn't require space to be smooth or continuous. It has no trouble describing fields that fluctuate wildly. But quantum mechanics has its own limitation. It assumes that the stage on which these processes occur is fixed and stable. It treats space-time as a background that does not react dramatically to the behavior of fields. when the background loses its stability, quantum mechanics becomes unreliable as well. This is where the two theories collide. Relativity insists that energy affects curvature. Quantum mechanics insist that energy must fluctuate. Put the two ideas together at small scales, and they begin producing conditions where the curvature of space-time should fluctuate violently in response to quantum activity. The more precisely you try to localize a region of space, the more energy you inject into that region. The more energy you inject, the stronger the curvature becomes. The stronger the curvature, the less meaningful the concept of localization becomes. It becomes a loop that cannot stabilize. Relativity tries to curve space-time smoothly. Quantum mechanics tries to shake it constantly. Neither theory can win. If you take relativity and push it close to the Planck scale, while still trying to treat space as smooth, the equations give infinite curvature in tiny regions. This suggests the creation of singularities on microscopic scales, not the kind produced by collapsing stars, but tiny ones born entirely out of fluctuations. But quantum mechanics doesn't allow those singularities to hold. Instead, it predicts that the fluctuations should disrupt them before they form fully. The result is an unstable environment where the predictions of one theory cancel or contradict the predictions of the other. This inconsistent behavior is a sign that neither framework is complete. Even though relativity breaks down in this extreme environment, it does so in a very informative way. The breakdown shows precisely where the assumptions of the theory fail. It shows that the idea of smooth space-time cannot continue indefinitely. It shows that the geometry of the universe must change character at small scales. And it shows that space-time must have some deeper structure that neither relativity nor quantum mechanics can fully capture. What's interesting is that the breakdown does not occur suddenly. It happens gradually as you move towards smaller distances. At scales where atomic structure dominates, relativity works flawlessly. At scales where quarks and gluons interact, relativity still works in most contexts even though quantum mechanics begins to dominate. But as you approach distances billions of times smaller than those within protons, the curvature predicted by relativity begins to change more rapidly in response to quantum fluctuations. The smoothness begins to wobble, the assumptions begin to crack, and at the Planck scale the cracks open enough that relativity can no longer be applied meaningfully. This shift from relativity to quantum rules is a transition between two regimes, not the disappearance of one or the other. Even at small scales, some aspects of relativity remain relevant. Even at large scales, quantum mechanics continues to operate, but the dominance shifts. At large scales, the curvature of space-time is smooth and continuous. At small scales, the fluctuations dominate, and the geometry becomes fuzzy or undefined. The Planck scale is the point where these two descriptions become incompatible. Some theories attempt to explain how the transition happens. One idea is that space-time is built from discrete units, and general relativity is an emergent approximation that arises when enough units work together. In this view, relativity is like a macroscopic description of a material. A metal bar looks smooth and solid, but under a microscope it's full of atoms that vibrate and interact. At a large scale, you don't see the vibrations. The bar seems rigid, but the rigidity breaks down at small scales where the atomic structure becomes important. Relativity might be similar. It works beautifully at large scales, but breaks down at scales where the discrete structure of space-time becomes relevant. Another idea is that gravity itself might be emergent. In this view, gravity is not a fundamental force but a statistical phenomenon arising from deeper microscopic behavior. If this were true, then relativity's smooth curvature would be like the flow of heat in a gas. At large scales, temperature and pressure behave predictably. At small scales, the motion of molecules becomes chaotic. If gravity emerges from underlying informational or thermodynamic principles, then the breakdown of relativity at the Planck scale would reflect the fact that the underlying structure does not support smooth curvature at small distances. Other ideas suggest that strings or extended objects represent the smallest meaningful structures, and relativity arises from the way those objects interact. In these approaches, the breakdown occurs because space-time cannot be divided into smaller points once you reach the size of the strings. The geometry becomes undefined because the objects defining it cannot be compressed further. Relativity's equations assume infinitesimal distances, but string theory replaces those distances with fundamental length. The result is a smooth, large-scale picture that dissolves into something else at small scales. Regardless of the approach, the idea remains the same. The Planck scale marks the point where relativity reaches the limits of its descriptive power. It shows that geometry, as relativity describes it, cannot remain meaningful. It must give way to something else, something governed by quantum rules that handle uncertainty and fluctuation better than relativity ever could. But these quantum rules must also include gravity, something ordinary quantum mechanics does not cover. This is why the search for a theory of quantum gravity continues. What's striking is that the breakdown of relativity at small scales mirrors the breakdown of classical physics at high speeds or low temperatures. Classical physics works fine for everyday events until speeds approach the speed of light. Then relativity steps in. Classical physics works fine for atoms until temperatures drop low enough for quantum effects to dominate. Then quantum mechanics takes over. In each case, the older theory continues to work as an approximation in its own regime, but the newer theory becomes necessary for describing the underlying structure. The same is true here. Relativity works perfectly at scales where geometry is smooth, but it must yield to quantum rules when the geometry becomes unstable. The point where relativity breaks and quantum rules begin is not a failure of physics. It is a sign that physics is layered. Each layer describes a different part of reality. Each layer emerges from deeper principles. Understanding where one layer stops and the next begins helps guide our search for those deeper principles. The Planck scale is not a barrier we can't cross. It's a clue about the structure beneath the surface. We arrive at a question that sits quietly behind many of the ideas we've explored so far. It's a question that seems simple at first, but the moment you begin to examine it more closely, it becomes surprisingly difficult to answer. Is space-time smooth, flowing without interruption the way we imagine a calm surface stretching to the horizon? Or is it pixelated, built from tiny, indivisible units that only appear smooth because they're too small for us to see? This question matters because everything we've discussed up to this point depends on what space-time really is. If space-time is smooth, then concepts like curvature, distance and direction apply in a continuous way. You can divide a distance in half and then in half again, and so on, without ever running into a smallest piece. If space-time is pixelated, then this picture falls apart. Distances cannot shrink beyond a certain point. Directions cannot be defined below a certain resolution. The geometry of the universe would have a minimum step size, something like the smallest tick on a ruler that reality allows. This isn't just an abstract philosophical issue. It affects how we understand gravity, the quantum world, black holes, the early universe, and the Planck length. It shapes how we imagine the foundations of everything we experience. And even though the question might seem like something we should already know, the truth is that physics has not yet reached a definitive answer. Instead, it offers clues, hints, and theories that lean in one direction or the other, with each perspective highlighting different parts of the puzzle. To approach this question gradually, it helps to begin with the everyday experience of smoothness. When you look at a table or a wall or a sheet of paper, everything appears continuous. If you run your finger along a polished surface, it doesn't feel like you're dragging it across a collection of separate units. It feels like one uninterrupted shape. Even when you zoom in with a microscope, the smoothness doesn't abruptly vanish. At first you see grain. Then at higher magnification you see molecules. Then, if it were possible to zoom further, you would see atoms. At each stage, the world looks less like a continuous whole and more like a structure built from smaller pieces. This pattern might make it tempting to assume that space-time will follow the same trend. Just as matter breaks into smaller components the more you look, maybe space also breaks into smaller components. Maybe the smoothness we experience is just a large-scale illusion that hides a pixelated microscopic foundation. But this comparison is only a starting point. Space is not matter. Time is not material. They don't behave like solids, liquids, or gases. They underlie everything, but they are not made of atoms the way matter is. And when you zoom in on space-time, the tools you need to investigate it change in fundamental ways. General relativity treats space and time as a continuous fabric. Its equations depend on derivatives, smooth changes, and well-defined geometry. To describe curvature, you need the ability to define how distances change from point to point. If space-time were made of discrete pieces, some of these mathematical tools would require modification, because they assume infinitesimal changes are meaningful. In a pixelated universe, infinitesimals would cease to exist. Changes would occur in finite jumps. This does not mean relativity would be wrong, but it would mean relativity would be an approximation that smooths over the underlying structure, much as the shape of a beach appears continuous even though it's built from individual grains of sand. Quantum mechanics, on the other hand, doesn't depend on smoothness in the same way. It introduces discreteness in the form of quantized energy levels, probabilistic outcomes, and wave functions that don't require space-time to be continuous. It doesn't force the universe to have small units, but it doesn't forbid them either. In fact, some interpretations of quantum mechanics suggest that a discrete structure underlies many quantum processes. But quantum mechanics also requires a background where probabilities evolve, and the simplest version of that background is a continuous space-time. Where things become complicated is when these two ideas meet. Relativity loves smoothness. Quantum mechanics tolerates both smooth and discrete backgrounds. But when we push them together near the Planck scale, neither framework can keep its preferred assumptions intact. Relativity expects infinitesimal distances. Quantum mechanics injects fluctuations. When those fluctuations become intense enough, the smooth surface predicted by relativity starts to fail, and that failure might be a sign that smoothness itself breaks down. If space-time is pixelated, the Planck length would be the size of the pixels. You wouldn't be able to describe distances smaller than that because the universe wouldn't have smaller units. You wouldn't be able to define positions with arbitrary precision because the positions themselves would come in discrete steps. This picture aligns well with the idea of a minimum measurable length. The Planck length would not merely be a boundary where our tools fail, it would be the smallest unit in the universe's construction. If space-time is smooth, on the other hand, the Planck length might simply mark the point where our current theories become inconsistent, without any deep physical significance beyond that. In such a world, space-time would continue to be continuous all the way down, but the mathematical tools we use to describe it would need refinement. New physics might reveal a smoother structure that avoids the contradictions of relativity and quantum mechanics without introducing discreteness. One argument often used to support a pixelated view comes from the behavior of black holes. The entropy of a black hole is proportional to the area of its event horizon. This suggests that the surface of a black hole contains a finite number of degrees of freedom, rather than an infinite number. If space-time were perfectly continuous, the surface would contain an infinite number of locations, each capable of storing information. But the calculations show that the entropy is finite. This implies that the surface might be composed of a finite number of units, each roughly the size of the Planck area. This idea fits well with theories that treat space-time as a kind of quantum geometry built from discrete pieces. These theories propose that space-time is made from loops, nodes, or other units that connect to form a network. At large scales, the network looks smooth because the number of units is enormous. At small scales, the discreteness becomes important. distances, areas, and volumes come in discrete amounts, much like the rungs on a ladder. The geometry flickers because the units interact in complex ways that don't produce stable shapes until enough units combine. But there are arguments in favour of smoothness too. One of them comes from string-based theories. In these frameworks, space-time remains continuous, but particles are replaced by tiny vibrating strings. The strings cannot be compressed beyond a certain limit, which prevents distances from becoming physically meaningful below that limit. This creates an effective minimum length without requiring space-time to be discrete. Instead, the minimum length arises from the behaviour of strings, not from the structure of space-time itself. The smoothness remains intact, but the tools we use to probe the geometry become limited by the physical properties of the strings. Another argument for smoothness comes from the mathematics of quantum field theory. The fields that describe particles exist on a continuous background. Many of the properties of these fields, such as their interactions, rely on this continuity. If space-time were pixelated, some of the tools used in field theory would require significant revision. This doesn't mean pixelation is impossible, but it does mean that any pixelated model must reproduce the predictions of quantum field theory at larger scales with remarkable accuracy. Given how precise those predictions are, the underlying structure would need to be extremely subtle. Some theories attempt to blend the two perspectives. They propose that space-time is smooth in the mathematical sense but discrete in the physical sense. In these models, the equations that describe space-time involve continuous variables, but physical processes cannot access values below the Planck scale. This would be similar to how a video file on a computer uses continuous mathematics to describe visual shapes, even though the actual images are displayed using pixels. The underlying physics wouldn't require space to be made of discrete units, but the observable effects would still produce a minimum resolution. Other models suggest that discreteness might emerge only at certain scales or under certain conditions. For example, space-time might appear smooth in regions where curvature is low and energy is evenly distributed, but become pixelated in regions of high curvature, such as near singularities or at the Planck scale. This would be similar to how certain materials develop grainy structures under pressure. The structure isn't always present, it emerges under the right conditions. There are also models where space-time is neither smooth nor pixelated in the usual sense. Instead, it emerges from a more abstract structure, where neither distance nor discrete units appear at the fundamental level. In these models, space-time is a derived concept that only becomes meaningful when a large number of underlying elements interact. In such a scenario, smoothness and pixelation are properties that emerge at different scales, but neither describes the fundamental level. This approach avoids the question entirely by suggesting that space-time itself is not fundamental. What makes this question so difficult is that we cannot directly probe the Planck scale. The energy required to measure such small distances would collapse the region into a microscopic black hole. This makes the question a matter of indirect evidence rather than direct observation. We look at how space-time behaves at larger scales and infer what might be happening underneath. We examine how theories behave when pushed to extreme limits. We analyse mathematical structures and see which ones produce consistent predictions. But until we find a theory of quantum gravity that successfully describes the Planck scale, the question remains open. Even though we don't know whether space-time is smooth or pixelated, exploring both possibilities offers insight into the boundaries of physics. If space-time is smooth, the universe must have a deeper structure that resolves the contradictions between relativity and quantum mechanics, while preserving continuity. If space-time is pixelated, the universe must have a discrete structure that becomes visible when distances approach the Planck length. Both possibilities challenge our intuition. Both possibilities require new ways of thinking. Both possibilities imply that space-time is more complex than it appears. What's comforting, even in the middle of this uncertainty, is that both views provide a consistent picture at the scales we experience. Whether space-time is smooth or pixelated at the deepest level, the large-scale structure looks the same. Planets orbit, light travels, clocks tick, and objects move in ways that match our everyday expectations. The universe remains stable and predictable at human scales, even if its foundation is filled with flickering or discrete units hidden far beneath the surface. As we keep moving through this journey into the smallest scales the universe allows, a natural question starts to grow quietly in the background. It's the kind of question that sneaks into the conversation once you've become familiar with the Planck length, the fluctuations of quantum foam, and the way gravity and quantum mechanics collide. The question is simple to phrase, but incredibly deep in its implications. Why can't anything be smaller than the Planck length? Why does the universe draw a boundary at this scale and refuse to go beyond it? This question isn't just about measurement. It isn't only about what our tools can or can't detect. It's about what distances even mean when we try to push them past the limits that the laws of physics define. It's about what happens to geometry, energy, and information when we attempt to shrink them past the boundaries laid out by the universe's constants. And even though the Planck length emerges naturally from those constants, it's worth asking why those constants combine in such a way that they create this lower limit at all. To approach this carefully, it helps to start with the concept of measurement itself. When we talk about distances, we assume that space exists in a way that allows us to define 2 points and talk about the separation between them. That seems simple enough. In everyday life, we can measure the distance between 2 objects easily. We can describe how far away 2 stars are from each other. We can calculate the distance between atoms inside a molecule. But every one of these measurements depends on the assumption that the geometry of space behaves predictably. This assumption works perfectly at large scales, and even at the scale of atoms and particles. But as we approach the Planck length, this assumption breaks down. The fluctuations introduced by quantum mechanics and the curvature introduced by gravity begin interacting in a way that destroys the stability of distances. The first reason nothing can be smaller than the Planck length is that distances stop being meaningful. Measurement is not just difficult, it becomes physically impossible. To measure a smaller distance, you would need to localize energy into a smaller region. But the more localized the energy becomes, the more uncertainty grows in its momentum. That uncertainty increases the amount of energy in the region, and when the energy becomes too large, it curves space-time so strongly that the region collapses into a tiny horizon. The moment you try to probe beneath the Planck length, you create the conditions for gravitational collapse. Instead of revealing smaller distances, you produce an event that hides whatever lies beneath the region you are trying to study. This reaction isn't a limitation of our tools, it's a limitation imposed by the universe. The laws of physics tell us that attempting to define a length smaller than the Planck length inserts so much energy into that region that the geometry itself breaks. The measurement destroys the space it attempts to describe. That fact outlines the second reason nothing can be smaller. Even if some deeper structure exists beneath the Planck scale, no method inside the universe can expose it without collapsing the region first. This collapsibility isn't just a curiosity, it's a direct consequence of the constants that define the universe. Newton's constant determines how strongly energy curves space-time. Planck's constant determines how energy must fluctuate at small scales. The speed of light defines how energy relates to geometry and motion. When all 3 constants work together, they impose a boundary on what can be resolved. This boundary is not arbitrary. It's built into the framework of the universe. But there is another way to think about why nothing can be smaller than the Planck length, and it has to do with the meaning of length itself. If space-time is made from discrete units or grains, then those units represent the smallest meaningful building blocks. If each unit defines the smallest area or volume, then distances smaller than the Planck length do not exist because the universe has no smaller pieces from which to form them. It isn't that space refuses to be measured, it's that space itself does not continue below that scale. Just as a piece of digital art cannot contain a half pixel, space-time cannot contain half of a unit. In this view, the Planck length exists because the universe cannot meaningfully define a smaller increment of geometry. It is not a limitation of a measurement, it is a limitation of reality. Another approach to understanding why nothing can be smaller involves the concept of information. In many theories, a region of space can hold only a finite amount of information. This idea emerges most clearly in discussions of black holes. Their entropy depends on the area of their horizons, not their volume. If the amount of information a region can contain is tied to its surface area, then there must be a smallest possible unit of area that corresponds to one bit of information. That unit is roughly the size of the Planck area. This means a region cannot be subdivided into arbitrarily small parts, because it would imply infinite information density. If the universe has a lower bound on information storage, then nothing can be smaller than that bound, because no smaller region can contain the information required to define its geometry or the processes that occur within it. A region smaller than the Planck length would not have the informational capacity needed to describe itself. That lack of capacity prevents such a region from existing as a meaningful part of space-time. Some theories propose that space-time emerges from deeper structures, and the Planck length corresponds to the level where these deeper elements become too sparse to form a recognizable geometry. In such theories, the idea of distance requires a large number of underlying relationships to stabilize. When the number of relationships becomes too small, the geometry loses coherence. If you try to push below the Planck length, you reach a point where the relationships cannot define a consistent structure. In that sense, the Planck length exists because geometry itself is an emergent property. This raises an interesting interpretation. Perhaps nothing can be smaller not because the universe prevents it, but because the universe does not provide the conceptual tools needed to describe smaller things. The notions of position, length, and geometry emerge only when certain requirements are met. When those requirements break down, the notions break down too. Another way to think about this limit comes from the energy required to probe small scales. To examine a region, you need to send something into it. In quantum mechanics, that something must behave like a wave with a wavelength small enough to resolve the features of that region. The smaller the wavelength, the higher the energy of the wave. When the wavelength becomes comparable to the Planck length, the energy becomes so intense that it significantly warps the region. You no longer illuminate the structure, you disrupt it. This leads to a paradoxical situation. The very effort required to see smaller distances destroys the distances. The region you're trying to probe collapses under the weight of its own energy. This collapse means that the universe enforces the Planck length as a boundary with physical consequences, not just conceptual ones. If relativity remained valid down to arbitrarily small scales, geometry could be defined indefinitely. If quantum mechanics remained valid without limits, energy fluctuations would continue shrinking distances. But combining both theories creates a threshold where each one cancels the possibility of the other pushing further. Relativity prevents extreme concentration of energy by creating curvature. Quantum mechanics insists on uncertainty that increases energy concentration. The two meet at the Planck scale and refuse to allow smaller distances. This is why nothing can be smaller. It's not that the universe doesn't have smaller components. It's that the definition of smaller stops being meaningful. The framework we use to describe size no longer functions in a consistent way. A length smaller than the Planck length cannot be measured, cannot be defined, cannot exist as an interval inside space-time. Even if a deeper structure exists, it does not manifest as a distance. Some theories propose that the Planck length acts as the smallest possible resolution of space-time. If you imagine the universe as something like a hologram, the resolution of the hologram determines how fine the details can be. You cannot display details below the resolution of the hologram because they simply cannot be represented. Likewise, space-time may not have the capacity to represent distances smaller than the Planck length. This analogy helps clarify the idea. The Planck length is not necessarily the size of the building blocks of space-time. It might be the smallest scale at which space-time can encode geometric information. Anything smaller would require a resolution the universe does not possess. Other theories suggest that space-time is continuous, but that the limits imposed by quantum mechanics and gravity create an effective minimum. In this picture, space-time could, in principle, have smaller distances, but no physical process could detect or influence them. They would be irrelevant to the physical behavior of the universe. If a feature cannot be measured, cannot influence outcomes, and cannot interact with the world, then it might as well not exist. The universe becomes indifferent to the idea of smaller distances. There is also the question of time. If the Planck length represents the smallest meaningful distance, then the Planck time represents the smallest meaningful interval. You cannot define events that occur in shorter durations, because no signal, no interaction, no fluctuation occurs on timescales shorter than this. This leads to another reason why nothing can be smaller. Time cannot subdivide further, and without a smaller time interval, there is no way for events that define smaller distances to occur. The limits on time enforce limits on space. One particularly interesting interpretation comes from the idea that the Planck length might be the scale at which space-time becomes dominated by quantum gravity effects. Below that scale, gravity is no longer a smooth curvature, but an unstable combination of quantum fluctuations. If space-time is a kind of pattern that emerges from deeper processes, then the Planck scale is the point where that emergent pattern dissolves. Trying to push beneath it is like trying to define the shape of a sound wave when the number of molecules involved becomes too small to support the wave. The concept breaks, not because the structure is forbidden, but because the structure stops being meaningful. In all these interpretations, the consistent theme is that the Planck length marks the boundary, where space-time as we understand it no longer exists as a continuous stable geometry. The concept of smaller distances collapses not because the universe contains no smaller structure, but because the structure cannot be described in terms of distance. This gives us a clearer sense of why nothing can be smaller. The Planck scale is where the idea of size itself dissolves. Below this scale, the geometry becomes too unstable, the information becomes too limited, and the physical processes required to define distances cannot exist. The universe is not hiding smaller distances. It simply does not support their definition. The journey gradually leads us toward a concept that may feel unfamiliar at first, but becomes more intuitive the longer you sit with it. It's the idea that information, not matter or space or energy alone, might be what ultimately defines the boundaries of the universe. This perspective has been growing quietly within physics for decades, supported not by speculation, but by calculations, thought experiments, and observations related to black holes, entropy, quantum mechanics, and the structure of space-time. The idea suggests that the universe may, in some sense, function like a kind of hologram, where the information describing a region is not stored inside it, but on the boundary that surrounds it. This sounds abstract when you first hear it, but the more you explore it, the more it connects with everything we've already discussed. The Planck length, quantum fluctuations, the behavior of gravity at small scales, and the question of whether space-time is smooth or pixelated, all converge naturally into a discussion about how information is stored, processed, and limited in the universe. And by understanding these limits, we begin to see why the universe cannot support smaller distances, deeper curvatures, or infinitely fine detail. To approach this gently, it helps to begin with black holes. They provide the clearest window into the relationship between information and geometry. A black hole is a region where gravity becomes so strong that nothing can escape, not even light. At first glance, you might think that once something falls in, its information is lost forever. But calculations from the 1970s onward showed something surprising. The entropy of a black hole is not proportional to its volume, as you might expect. It is proportional to the area of its event horizon. This is a profound result. It means the amount of information a black hole can contain is limited by the size of its surface, not the space inside it. This idea was unsettling when it first appeared because it contradicted our intuition. We're used to the idea that volume determines capacity. A larger container holds more water, a larger room holds more air. But black holes ignore this logic. Their information capacity grows with area, not with volume. If you double the surface area, you double the maximum amount of information the black hole can store. The interior doesn't matter, it's the surface that counts. Physicists began wondering whether this was an odd property of black holes, or whether it reflected something deeper. Over time, the evidence pointed toward the deeper interpretation. Black hole entropy seemed to reveal a more universal principle. It implied that the amount of information any region of space can hold is limited by the size of its boundary, not by the amount of empty space inside it. This is a striking idea because it suggests that information storage in the universe doesn't depend on filling a region but on covering it. This leads to what became known as the holographic principle. It suggests that the maximum amount of information contained within a region of space is encoded on the boundary that surrounds it. This is similar to how holograms on credit cards or identification badges store a three-dimensional image on a two-dimensional surface. The image appears to have depth, yet all the information needed to reconstruct that image lies on the surface. The holographic principle proposes that something faintly similar could be happening in the universe. This doesn't mean the universe is literally a hologram in the digital or optical sense. It doesn't mean the world is fake or illusory. Instead, it means that the geometry and physical processes inside a region may be limited by how much information can be encoded at its boundary. This connects directly with the Planck scale. If each unit of the boundary can store a finite amount of information, and that unit is roughly the size of the Planck area, then the interior cannot contain more than a specific number of information units. This creates a physical limit on detail. It prevents arbitrarily small structures from forming. It stops distances from shrinking without bound. This provides one explanation for why nothing can be smaller than the Planck length. The universe cannot encode the information needed to define distances below that scale. A region that is smaller than a Planck area cannot support a meaningful amount of information. It doesn't have enough capacity to define geometry, motion, fields, or events. If information capacity is limited, then geometry is limited too, because geometry cannot be described without information. This idea brings a new perspective to everything we've discussed. The quantum foam that appears at the Planck scale may be a sign that the information content of tiny regions fluctuates between possible microstates. The flickering grain of space-time may be the physical expression of discrete information units rearranging themselves. The unruly behavior of gravity at small scales may reflect the fact that the information capacity becomes saturated, pushing the region toward collapse. And the strange marriage of constants may be telling us that information, not distance, is the most fundamental concept. If this is true, then the smallest scales of the universe aren't limited by geometry alone. They're limited by information. Space and time may emerge from the ways information is arranged and processed. When enough information accumulates in stable patterns, space-time appears smooth. When the patterns become unstable, space-time flickers. When the patterns cannot support continued structure, space-time dissolves. Some approaches to quantum gravity build explicitly on this idea. They treat space-time as an emergent phenomenon that arises from the interactions of microscopic informational elements. These elements aren't geometric points or particles. They're more like logical units or relationships. Geometry arises when enough relationships form stable patterns. The Planck scale appears when the number of relationships becomes too small to support geometry. Under this view, space-time is not something that exists independently. It is the large-scale behavior of a deeper structure. This deeper structure might not involve space or time in any conventional sense. Instead, it might involve networks of interacting elements whose collective behaviour produces the geometry we experience. The limits on these networks may produce the limits on space-time, including the Planck length. Another perspective comes from quantum entanglement. In recent decades, physicists have explored the possibility that the structure of space-time is rooted in entanglement patterns. Entanglement connects particles or systems in such a way that information about one system cannot be fully separated from information about another. If enough entanglement exists between different regions, space-time appears connected. If entanglement decreases, space-time begins to fall apart. In extreme cases, geometry might dissolve entirely when entanglement becomes insufficient. This offers another reason why space-time cannot exist below a certain scale. The necessary entanglement patterns cannot be arranged in such small regions. These ideas about information also help explain why relativity and quantum mechanics collide at the Planck scale. Each theory implicitly assumes something different about information. Relativity assumes that information can be encoded smoothly across space-time. Quantum mechanics assumes that information is encoded in discrete states that fluctuate. When the scale shrinks toward the Planck length, these assumptions become incompatible. The amount of information required to encode smooth geometry cannot fit into the region. The information encoded by quantum processes fluctuates too strongly to support curvature. Both theories reveal their limitations because the information capacity of space-time becomes the limiting factor. The holographic perspective also helps clarify why distances and time intervals cannot be made smaller. If information content grows with area, then any attempt to define a smaller region reduces the amount of information it can hold. At a certain point, the region becomes too small to define positions, directions, or durations. Without the information needed to describe an event, the event cannot exist in the usual sense. This limitation is not about technology or observation. It is about the structure of the universe. This perspective gives a different meaning to the Planck length. Instead of viewing it as a physical object or a grain of space-time, we can view it as the smallest possible unit of information storage. It is the resolution of the universe. Just as a screen has a certain number of pixels per inch, the universe may have a certain amount of information per unit of area. You cannot define a feature smaller than a pixel on a screen, because the screen cannot encode it. Similarly, you cannot define a feature smaller than the Planck length, because the universe cannot encode it. Another way to think about this is to imagine drawing a picture on a digital display. If you zoom in far enough, you will see that the picture breaks into pixels. You cannot draw a line thinner than 1 pixel, because the display has no smaller elements. But you also cannot draw two different shapes that occupy the same pixel without ambiguity, because the pixel cannot represent both shapes at once. Similarly, space-time cannot encode multiple distinct locations inside a region smaller than the Planck length. The information capacity is too small. If the universe functions this way, then space-time becomes a large-scale phenomenon that only appears smooth because the resolution is incredibly fine. The smoothness is an illusion created by the blending of many informational units. This does not make space-time less real. It simply means that its realness arises from deeper structures. In some models, the holographic principle isn't just a metaphor but a literal mathematical equivalence. It suggests that the physics inside a region can be rewritten entirely as physics on the boundary. The interior and the boundary contain the same information expressed differently. In such models, space-time inside the region emerges from the behavior of fields on the boundary. Geometry arises from the distribution of information at the edge. Distances and time intervals are encoded indirectly. If this is the case, then the interior of the universe may be a projection of relationships defined elsewhere. This perspective connects with why certain theories predict that space-time at small scales doesn't behave like a traditional geometry at all. If geometry is encoded indirectly, then geometry cannot exist without enough information to support it. When the available information becomes too small, the geometry breaks apart. That breakdown occurs naturally at the Planck scale. The holographic perspective also helps explain why black holes behave the way they do. Their surfaces act like storage limits. When something falls in, the surface area increases to accommodate the new information. The interior might not store information in the classical sense. Instead, the boundary encodes everything. This reverses our intuition about where information should reside. It suggests that boundaries are more fundamental than volumes. This inversion provides a way to understand why nothing can exist smaller than the Planck length. If information is tied to area, and the smallest meaningful area is the Planck area, then no region can contain information smaller than that. Without the information needed to define geometry or state, nothing can be smaller. The universe enforces this not through force, but through the rules that govern information. Even though the holographic principle may sound surprising, its implications align well with the limits we encounter when studying the Planck scale. The collapse of measurement, the violent fluctuations of quantum foam, the breakdown of curvature, the limitations of information storage, and the finite resolution of space-time all point to the same boundary. They all suggest that there is a fundamental limit on how much detail the universe can encode. This doesn't make the universe rigid or simple. The information capacity of even a small region is enormous. The holographic principle doesn't imply a lack of richness. It implies a limit, not an absence. The world can be as detailed as it is because the scale where detail stops is incredibly small. But the existence of that limit ensures that physics does not collapse into contradictions when pushed toward extremes. There's a question that tends to surface almost naturally, almost quietly, once the Planck length becomes familiar. It's a question that can feel a little unsettling the first time you encounter it, because it challenges so many assumptions about what the Planck scale represents. After spending time learning how the constants combine, why geometry breaks down, how holography limits information, and how the quantum and gravitational worlds collide at small distances, it becomes natural to wonder whether the Planck scale is truly a boundary of nature, or whether it's a boundary created by the theories we use. Could the Planck scale be an illusion? Not an illusion in the sense of being false or imaginary, but an illusion in the sense that it might not be a fundamental feature of reality, but rather a feature of the frameworks we currently rely on. This question isn't meant to undermine the Planck scale or remove its significance. The Planck length, Planck time, and Planck energy remain useful and meaningful in every modern theory that studies quantum gravity. But asking whether the Planck scale is an illusion means exploring whether the limits we see are reflections of actual physical boundaries or artifacts created when our theoretical descriptions meet their natural limits. It's a subtle question, and it opens many doors. To explore this, it helps to start with what the Planck scale actually is. It's not something that was discovered through experiment. It didn't appear in the data from a telescope or from particle collisions. It emerged from mathematics. When you combine the speed of light, Planck's constant, and Newton's gravitational constant in certain ways, you obtain quantities with the dimensions of length, time, and mass. Those quantities form the Planck scales. They're not measured, they're derived. The fact that they have physical meaning is something physicists inferred by studying how gravity and quantum mechanics behave at small distances. This raises a possibility. Perhaps the Planck scale marks the point where our current theories break down because of the way those theories are constructed. The constants define limits, but the limits may apply only to the theories that contain them. For example, in classical physics before quantum mechanics was discovered, people believed that energy could be distributed continuously, but the Planck constant later revealed that this belief was a feature of the classical picture, not of nature itself. The classical description wasn't wrong in its domain, it simply wasn't complete. In a similar way, the Planck scale might reflect the breakdown of our current descriptions rather than a breakdown of space-time itself. When we talk about distances smaller than the Planck length becoming meaningless, we may be describing the limits of relativity in quantum mechanics, not the limits of reality. We don't yet know whether reality stops at those scales or whether our tools stop there. One idea that supports this possibility is that the Planck scale could be a boundary created by the limitations of measurement, not the limitations of geometry. To measure a small distance, you need high energy, but at a certain point the energy becomes so concentrated that it collapses the region, creating a horizon. This collapse prevents us from learning anything about smaller scales. But this doesn't necessarily prove that smaller scales don't exist. It proves that we cannot access them using the tools and rules available to us. It's similar to trying to observe details inside a region hidden behind a horizon. The details might exist, but no signal can bring them out. Another way to think about this is to consider how often in the history of science, the boundaries of knowledge appeared absolute until new frameworks shifted those boundaries. Before quantum mechanics, it seemed impossible that energy could behave in discrete steps. Before relativity, it seemed impossible that time could stretch or that length could contract. Before thermodynamics, it seemed impossible that temperature and pressure could emerge from random microscopic motions. At each stage, the limits of the earlier theories created illusions about what was possible. When new theories arrived, those illusions disappeared. The Planck scale might be similar. The limits imposed by relativity and quantum mechanics might be illusions that vanish when a deeper framework is discovered. If space-time arises from more fundamental elements that do not involve distances or durations at all, then the Planck length and Planck time might be emergent, not fundamental. They may reflect the resolution of the emergent structure rather than the smallest units of the true underlying reality. This possibility appears in theories where space-time is not fundamental. If space-time emerges from entanglement, information networks, or algebraic relationships, then the Planck length might represent the scale at which these emergent structures lose coherence. It may be the point where space-time stops being a useful concept, not the point where reality stops having structure. In this view, the Planck length is the smallest meaningful unit of emergent geometry. But the underlying processes might operate on scales that do not correspond to distances or times in any recognizable way. Consider an analogy. Imagine a pattern created by a grid of pixels. The pixels are fundamental to the image, but the shapes and curves that appear on the screen are emergent. If you zoom in, the curves break into steps. The resolution of the display determines how fine those steps can be. To an observer who doesn't know about the underlying screen, the resolution limit might appear to be a fundamental boundary of the world, but the screen itself might be made from even smaller units. The image is an emergent phenomenon, and the resolution is a limit of the emergent pattern, not a limit of the underlying device. If space-time is emergent, the Planck scale could be the resolution limit of the emergent space-time, not a physical minimum. Reality might operate at a level that has no distances, no durations, and no geometry at all. In that case, looking for distances smaller than the Planck length might be like looking for subpixels in a display. They don't exist in the emergent picture, but the underlying mechanism might be far more detailed. One interpretation of the holographic principle fits well with this idea. If the information describing a region of space is encoded on its boundary, then space-time inside that region may be an emergent phenomenon. The smoothness, curvature, and causal structure of space-time might result from the way information is arranged on the boundary. In that case, the Planck scale could be the smallest meaningful unit of area on the boundary, but the underlying reality might not involve space or area at all. In some models, the underlying reality could be a network of abstract relationships, something like a mathematical graph or a set of entangled quantum states. These relationships might not have spatial meaning. They might not involve distances or geometry. They might simply exist as connections. Space-time would appear when these connections organize in certain ways, similar to how temperature appears from the motion of molecules. If this is true, then the Planck scale might reflect the limits of the geometric picture, but not the limits of the underlying structure. The true reality might not operate in terms of the length or time at all. Another idea supporting the illusion perspective comes from approaches where the Planck scale marks a phase transition. In some models, space-time behaves one way at large scales and another way at small scales. But the transition between these regimes might not represent a fundamental barrier. It might be similar to how water behaves in different phases. At certain temperatures, water becomes ice. At others, it becomes vapor. The transitions don't reflect limits on what water is. They reflect limits on how certain variables interact. The Planck scale might be the temperature in this analogy. It marks the transition between space-time behaving as a smooth geometry and space-time dissolving into something else. But the something else might contain deeper structure. Some theories propose that space-time is continuous but becomes unstable at the Planck scale because quantum fluctuations overwhelm the geometry. In this interpretation, the Planck scale might reflect the limit of stability, not the limit of reality. Distances smaller than the Planck length might exist mathematically, but they might not correspond to stable physical states. This is similar to how certain wavelengths of sound cannot propagate in certain materials. The sound waves exist mathematically, they're just not supported physically. If space-time cannot support stable geometric patterns below a certain scale, then the Planck length emerges naturally, but it doesn't prove that smaller scales are meaningless. Another approach suggests the opposite. Space-time might be discrete at the smaller scales, but the Planck length might not represent the size of the units. Instead, it could represent the scale at which discreteness becomes visible to our theories. The underlying units might be far smaller, but their influence might average out until distances approach the Planck scale. Only then would the discreteness become noticeable. This is similar to how the atomic structure of matter is invisible at large scales, but becomes important at small scales. The Planck length might be the scale where the atomic structure of space-time becomes relevant, but the atoms of space-time might be smaller still. There is also the possibility that the Planck scale is not universal. Some theories propose that the Planck length depends on energy or environment. In certain extreme conditions, the scale at which space-time breaks down might shift. This would mean that the Planck length is not a fixed boundary, but a dynamic one. It would be a scale that emerges from the interplay of forces, not a scale baked into the universe itself. Such models challenge the idea that the Planck length is absolute. When physicists ask whether the Planck scale is an illusion, they aren't suggesting that it isn't important. They're exploring whether its significance lies in the universe itself or in the theories we use to describe it. The distinction is subtle but meaningful. A boundary created by nature would reflect something fundamental about the fabric of reality. A boundary created by theory would reflect something fundamental about the tools we use. Even if the Planck scale turns out to be an artifact of our theories, it still plays a crucial role in guiding those theories. It tells us where quantum mechanics and relativity become incompatible. It tells us where geometry becomes unstable. It tells us where our current descriptions reach their limits. These limits may not represent the end of reality. They may represent the beginning of something deeper. What remains comforting in all of this is that the universe behaves beautifully at the scales we inhabit. Whether the Planck scale is a fundamental boundary or a reflection of deeper structures, the world above it works in ways that are stable, predictable, and consistent. Whatever lies beneath the Planck scale, whether geometric or non-geometric, discrete or continuous, emergent or fundamental, it supports the reality we experience. Up to now, we've been asking what happens as we approach the smallest distances the universe allows, what the limits mean for measurement, how information shapes those limits, and even whether the limits themselves might be illusions created by theory. But behind all of this is a more basic question, one that invites us to reconsider the way we think about reality. If space truly has a minimum size, what does that mean for the very idea of existence? What does it mean for something to be somewhere when somewhere cannot be made any smaller? What does reality look like when the fabric of the universe stops being divisible and instead arrives at a smallest meaningful grain? This question can feel abstract at first, but only because we're so accustomed to thinking of space as something that stretches smoothly in every direction, without interruption. For most of our lives, space feels infinite not only outward, but inward as well. You can zoom in on a surface, zoom again, and then zoom further still, expecting detail after detail to continue emerging at each scale. The idea that space might have a smallest meaningful unit interrupts that intuition. It suggests that zooming in eventually stops not because you reach a physical barrier, but because the concept of zooming loses meaning. This shift in thinking requires a gentle approach, because the idea of a minimum size pushes against many of the assumptions we carry without ever noticing them. One assumption is that reality is made up of things sitting in places. A table is in a room, a planet is in orbit, a particle is in a region. But if regions cannot be made arbitrarily small, then the entire framing of being in a place begins to change. Space becomes something like a lattice of possible locations, or a collection of minimum-sized units that cannot be subdivided. And if those units flicker, rearrange, or emerge from deeper processes, then the concept of place becomes something far less literal than the one we use in daily life. To ease into this, it helps to start with the simplest version of the idea: the minimum area or minimum volume that can exist according to different approaches to quantum gravity. Some theories propose that the smallest possible area is one measured in units of the Planck area. That would mean a surface cannot contain meaningful detail below that scale. Others propose that volumes come in discrete steps, each representing the smallest chunk of space. These volumes wouldn't be empty containers, because emptiness itself would need to be defined by the underlying grain. Instead, they would represent bits of geometry, much like individual tiles in a mosaic. If space behaves like this at its deepest levels, then reality doesn't stretch continuously downward. It isn't a smooth canvas that can be carved into infinitely finer regions. It's more like a structure built from countless tiny units that combine to form the larger shapes we experience. When we move through the world, we glide across this structure without noticing its smallest steps. In the same way our hands feel a piece of paper as smooth even though the paper is built from fibers. Each fiber is far smaller than our sense of touch can detect. And if you zoomed in far enough, even the fibers would reveal their own grain. But the difference here is that space-time's grain isn't made of stuff. It's not made of atoms or molecules. It's made of geometry itself. Reality at this level doesn't consist of objects placed in space. Instead, space is part of the object's definition. The grain is not the material. The grain is the very structure that lets matter and energy have positions at all. This has several consequences for what it means for something to exist. One consequence is that position cannot be defined more precisely than the smallest unit of space. You cannot say that an object is located at a region smaller than a Planck-sized unit, because the universe cannot store enough information to specify such a location. If something appears to have a location smaller than that, the appearance is an illusion created by larger-scale effects. The minimum grain hides beneath the smoothness of the macroscopic world. This doesn't mean objects are fuzzy or that reality becomes vague. Instead, it means precision has a fundamental limit. Knowing an object's position more precisely than the size of a minimum grain would require more information than the universe can encode. And since information is tied to area or to connections between microscopic degrees of freedom, the capacity simply isn't there. This makes existence itself something like a state that occupies a minimum region. You can define where something is within that region, but you cannot define its location more finely. Another consequence is that motion changes in subtle ways. In a continuous space-time, motion can be thought of as a smooth path that traces out a line from one point to another. But if space has a minimum size, a smooth line doesn't truly exist at microscopic scales. Instead, the line becomes a sequence of transitions between minimum regions. The transitions are so small and happen so quickly that they blend into a smooth curve at the scales we experience. But the underlying steps form the true path. This doesn't violate the idea of motion. It simply means motion is emergent rather than fundamental. If space has a minimum size, then velocity also becomes something that exists only at scales above that size. At the level of the minimum grain, the idea of velocity may dissolve, because to define velocity, you need to define distances traversed in intervals of time. If distance cannot shrink below a certain value, and time cannot shrink below a certain interval, then velocity becomes a quantity that emerges when many transitions accumulate, not something defined instantaneously. This idea isn't as unusual as it sounds. Many physical quantities emerge from coarse-grained behavior. Temperature emerges from the average energy of molecules. Pressure emerges from the collective momentum of molecules hitting the walls of a container. In both cases, the underlying microscopic processes don't contain the macroscopic concepts directly. They produce them when enough interactions occur together. Velocity might work similarly. At scales where space and time become discrete, the concept of velocity dissolves, and at larger scales it reappears smoothly. Another aspect of reality that changes when space has a minimum size is the concept of scale itself. In a continuous space-time, you can zoom in indefinitely. There is always another level beneath the one you're studying. But if space has a minimum size, zooming eventually stops. Instead of a continuous hierarchy of smaller and smaller structures, you arrive at a foundational level where further subdivision doesn't make sense. That foundational level may not look anything like the space we experience. It may resemble a network, a pattern of relationships, a set of connections, a structure of entanglement, or something even more abstract. This doesn't reduce the richness of the universe. Instead, it changes where the richness comes from. Instead of emerging from infinite detail, it emerges from the ways the minimum units connect and interact. Complexity arises from combinations, not arbitrarily small components. This is similar to how languages arise. Letters are small and finite. Their combinations, however, produce entire libraries of meaning. The universe might work similarly. A small number of fundamental informational or geometric units might combine to produce the vast complexity of the cosmos. One of the more subtle consequences of a minimum size of space is that the idea of continuity becomes something of a large-scale illusion. The continuity we experience in everyday life is not a direct property of the world. It is a property of how our senses and our theories interact with bundles of minimum regions. When millions or billions of these regions behave coherently, the appearance of smoothness emerges naturally. This doesn't make the smoothness less real. It simply means the smoothness is the macroscopic behavior of something that stops being smooth at its deepest levels. Another consequence relates to causality. In a continuous space-time, causality is defined through smooth curves that connect events. If space-time is grainy, causality might instead be defined through sequences of informational exchanges or transitions between minimum regions. The causal structure would still exist, but it would emerge from the way the grains connect. Time would still flow, but the flow would arise from transitions between discrete intervals rather than from a smooth continuum. This idea connects with the Planck time, the smallest meaningful interval. When time has a minimum step, events cannot occur within intervals smaller than that. But this doesn't make time choppy or broken. It just means that the microscopic foundation of time consists of units rather than an unbroken line. At macroscopic scales, these units blend together into the steady flow we experience. The ticking of time becomes continuous only when the units are too small for us to distinguish. Another way that reality changes when space has a minimum size involves fields and forces. The fields we use to describe matter and energy are continuous in standard quantum field theory. They assign values to every point in space, but if space does not contain an infinite number of points, fields must be reinterpreted. Instead of assigning values to continuous positions, fields would assign values to the minimum regions of space. Their behavior would depend on how those regions connect and how the values change from one region to another. Smooth fields would be large-scale approximations. The underlying behavior would be step-like or relational. This doesn't make fields less powerful as tools. It simply means fields encode large-scale behavior rather than microscopic structure. The deep structure might be something else. something like patterns of information or networks of entanglement, and fields emerge as effective descriptions at higher levels. There is also an important shift in how we think about energy. If space has a minimum size, then energy cannot be localized beyond that size. This means any attempt to place too much energy into a region of space smaller than the minimum will cause the region to collapse or lose its geometric meaning. This ties directly into the idea of black hole formation at small scales. It also implies that energy density has a maximum meaningful value. Above that value, the structure of space-time dissolves or reorganizes. This offers a different view of the relationship between energy and geometry. Instead of being continuous partners, they become partners that only operate within the limits of the information capacity of space-time. Another consequence relates to what it means to observe something. Observation requires distinguishing one state from another. Distinguishing states requires information, and if regions of space have limited information capacity, then the distinction between states becomes limited as well. This doesn't reduce the richness of what can be observed at normal scales. It simply means that deep down, reality contains only a finite number of distinguishable states in a given region. When we try to describe more than that, we hit the limits imposed by the Planck area or Planck volume. These limits don't prevent physics, they prevent contradictions. If reality is built from minimum size units of space, then existence becomes something like occupying a unit in a vast interconnected structure. At large scales, this structure feels continuous, but at small scales it reveals its discrete nature. Events become sequences of transitions between units. Motion becomes a reorganization of connections. Fields become patterns defined over units. Forces become interactions between units. Geometry becomes the structure that emerges from how units connect. This changes how we think about scale, distance, and continuity, but it preserves everything we know about large-scale physics. The sun still curves space-time. Planets still orbit. Atoms still hold together. Light still moves in predictable ways. The presence of a minimum size does not disrupt the larger world. It simply defines the limits of the smallest world. What becomes most interesting about this idea is not the restrictions it imposes, but the possibilities it opens. If space-time has a minimum size, then it is not a fundamental ingredient of the universe. It is something built from deeper structures. Those structures might not resemble space or time. They might not have geometry. They might not obey familiar rules. Instead, they might be informational, relational, or algebraic. This shifts the question of reality from what is space made of, to what process gives rise to space. When space has a minimum size, reality becomes something more layered. The world we interact with emerges from deeper rules. Those rules might produce geometry only when enough units accumulate. They might produce continuity only when enough transitions blend together. They might produce causality only when enough patterns link sequentially. This makes the Planck scale not a barrier but a threshold. Above it, reality looks like the universe we know. Below it, reality might look entirely different, governed by rules that do not involve distance or direction. And those rules, whatever they are, must be rich enough to build everything we see. As we slowly begin to drift back from the smallest edge of reality, where distances blur and geometry dissolves and nothing remains quite the way it once seemed, there's a certain calmness that arises almost naturally. It's the kind of calm that appears after spending a long time looking at something incredibly intricate, then gently stepping away while its details linger quietly in the back of your thoughts. The quantum horizon, that place where the familiar idea of space-time finally gives way to something more fundamental, isn't a boundary marked by walls or barriers. It's more like the edge of a landscape where the shapes become too fine to trace and the features begin to blend into something that no longer behaves in the ways we expect. Pulling away from that horizon gives the mind a chance to take a slower breath, to adjust back to a world built from larger patterns that remain steady even while the microscopic world underneath continues its restless shifting. The journey toward the Planck scale has shown us that the universe is far more layered than it appears at first glance. We've followed the scales downward, step by step, until the smoothness of space dissolved into grains, fluctuations, or deeper structures that don't resemble geometry at all. We've watched gravity lose its composure as the quantum world shakes its foundation. We've seen how information might sculpt the boundaries of what can exist, and we've considered the possibility that the Planck scale itself might be a limit of our tools rather than a limit of reality. Now, as we gently move upward again, returning to scales where space-time regains its calm and curvature becomes smooth once more, the perspective shifts subtly. The way a distant cityscape looks different when you begin walking back toward it from above a high hill. Moving away from the quantum horizon reveals something important. The world we experience every day doesn't require us to know the microscopic truth about space-time. We can live entire lives without ever needing to consider discrete units of geometry or the limits of measurement defined by the Planck length. Yet the existence of those limits shapes everything anyway. They define how fields behave, how particles exist, and how matter organizes itself. Every object we see rests on the foundation of rules that operate at scales far smaller than anything we can touch or perceive. The stability of the familiar world is built from the instability of the microscopic one. Without uncertainty, fluctuations, or the strange interplay between gravity and quantum mechanics, the macroscopic world would not hold together. As we drift upward through these scales in our thoughts, the quantum foam beneath reality smooths out. At slightly larger distances, space-time stops flickering so violently. The fluctuations that once disrupted geometry merge into a steadier pattern, the way waves blend into a flat surface when observed from far enough away. The tiny distortions that once dominated make room for the continuous curvature described by relativity. At these scales, distances become meaningful again. Directions settle, geometry stabilizes. The chaotic behavior near the Planck length becomes the hidden foundation supporting the smooth world above it. This shift isn't sudden, it's gradual. If you could watch space-time transition from the quantum regime to the classical one, you wouldn't see a line marking where one ends and the other begins. You'd see something closer to a landscape that becomes clearer as the fog lifts. One moment the fog obscures every detail, making shapes unsteady. The next moment gentle outlines appear. Then the details sharpen, and eventually the entire scene takes form. Moving away from the Planck scale is like watching that fog lift. Patterns that once seemed impossible to define slowly emerge as stable features of the world. Geometry comes together the way a picture emerges from a mosaic as you step away from it. At larger scales, time also regains its familiar flow. Near the Planck time, durations become so short that nothing can happen within them. Events overlap in ways that prevent any meaningful order. But as we move outward, the flickering of time structure slows into something more recognizable. Durations stretch, separating one moment from the next. Sequences begin to form. The notion of before and after becomes meaningful again. Time starts to feel like a stream rather than a sequence of discrete intervals. By the time we reach scales familiar to atoms, time has taken on its usual role, connecting events in a way that lets processes unfold and interactions develop. We often think of reality as something uniform, but the transition between small and large scales shows that reality is layered. What we see on the surface is just one layer of a deeper structure. These layers aren't separate worlds, they're different expressions of the same underlying rules. The laws of physics don't change as we move from one scale to another. Instead, their consequences change. At small scales, the uncertainty principle shapes the world. At large scales, curvature and motion shape it. And in between, there is a kind of crossover where both sets of rules influence the behavior of matter. The interesting part is that the boundary between these regimes is not a place where physics stops. It's a place where physics transforms. Roads don't end at the quantum horizon. They simply become too narrow and unsteady for our usual ways of thinking. As we move back toward the scales where matter behaves predictably and fields stabilize, the tools we use, equations, measurements, concepts, become reliable again. They realign with the structures they're meant to describe. Our sense of scale becomes intuitive again. Lengths, areas, and volumes make sense. Geometry stops slipping out from beneath us. This steadying of the world feels quietly reassuring. After travelling through regions where distances become uncertain and time loses coherence, the familiar world takes on a different tone. It feels more grounded, more stable. It's a reminder that the universe doesn't need us to understand its smallest layers in order to let us live within it safely and comfortably. The large-scale world is generous in that way. It offers predictability built from unpredictable foundations. It offers order built from fluctuations. As we drift further upward in scale, particles begin behaving in ways we find more comfortable. Instead of the chaotic interactions that dominate in the quantum realm, stable patterns begin to emerge. Quarks bind into protons and neutrons. Those protons and neutrons gather into atomic nuclei. Electrons settle into stable orbitals. The wildness of quantum fluctuations becomes the framework that allows structure to exist. Without those fluctuations, stable orbitals wouldn't form, atoms wouldn't be possible, and without atoms, everything built from them, molecules, cells, planets, and the entire visible universe, would vanish. It's interesting to think about how stability arises from motion. Inside atoms, particles never sit still. Their positions and energies fluctuate constantly. Yet those fluctuations create stability. They prevent collapse. They create balance. Returning from the Planck scale makes this relationship clearer. Stability doesn't appear despite the fluctuations. It appears because of them. The unpredictability of the quantum world is exactly what allows the macroscopic world to remain predictable. As we shift further outward, the geometry of space becomes even more stable. Space-time curvature becomes smooth enough for relativity to take full effect. Gravity begins behaving like the calm, predictable force we experience every day. Planets orbit stars along paths shaped by smooth curvature rather than flickering geometry. The way light bends around massive objects becomes something we can describe with confidence. Time dilation and gravitational effects become measurable but gentle. The violent curvatures seen near the Planck scale become nothing more than mathematical curiosities when viewed from this distance. And as we climb even higher, the quantum horizon fades entirely behind us. Space becomes so smooth that the idea of its graininess no longer has any visible effect. Time becomes so steady that the Planck time becomes irrelevant. The microscopic fluctuations continue to exist, but their influence is now faint, quiet, and hidden deeply beneath the layers of larger behavior. This is the world where scales merge into the familiar environment where life unfolds. As we return to the sizes where biological processes occur, the influence of the Planck scale becomes invisible. Proteins fold, cells divide, signals move along neurons. None of these processes require the smallest units of geometry to be directly involved. They rely on the large-scale stability created by the averaging of countless microscopic interactions. The entire structure of life emerges from physics that operates far above the quantum horizon. Yet that horizon still shapes the foundation beneath it, supporting the world from below the way roots support a tree. Moving further into everyday scales, the large structures of the universe begin to take shape again. Mountains stand firmly, water flows, clouds move. The world behaves in ways that are fully consistent with the laws of classical physics. Those laws aren't wrong. They're simply approximations that become incredibly accurate at large scales. They offer a picture of nature that feels intuitive because it aligns with our senses. We live in a world that operates far above the Planck scale. Our biology evolved to interact with matter at sizes where geometry is smooth and predictable. Our intuition reflects that. As we drift even further outward, the scales grow enormous. Planets glide through space. Stars shine steadily. Galaxies swirl into vast spirals. The expansion of the universe stretches across billions of light years. Everything seems calm and orderly. Yet all of this structure, all of the stars and galaxies and filaments of matter, depend on the tiny scale rules we explored earlier. Without the minimum size of space-time, without the uncertainty that shapes atoms, without the information limits encoded in surfaces, none of these structures would form. The universe's largest patterns rely on the smallest constraints. The deeper we journey back outward, the more surprising it becomes that the smallest scales can influence the largest ones so profoundly. It shows how interconnected the layers of the universe are. It shows how the flickering geometry beneath everything supports stable worlds. And it shows how the Planck scale, even if it's not a fundamental boundary, remains a guide to understanding how space-time behaves. Returning from the quantum horizon doesn't erase the strangeness of what we encountered. Instead, it frames that strangeness within the larger context of a universe that balances unpredictability with stability. It reminds us that reality doesn't need smoothness at every level. It needs consistency at the level where life unfolds. It needs predictability where structures grow. It needs continuity where motion happens. Those needs are met by the way the universe transitions from the quantum to the cosmic. As we move further out, letting the quantum horizon settle into memory, the world feels familiar again, but familiar in a deeper way. The next moment, the next thought, the next breath, all unfold within the space-time built from the shaky foundations we explored. Everything is grounded in something far more intricate than it appears. The universe offers simplicity on the surface only because it contains complexity at its core. And as this drift continues, the scales widen until the smallest units begin to feel distant, like details in a story that happened long ago but still influence everything that followed. The quantum horizon remains out there, far below the world of stars and cells and ordinary motion, shaping everything quietly from beneath, while the universe carries on in the gentle, steady way that allows us to exist within it.